Ok. Attends, où est-ce qu'il est zoom? Ouais, c'est Nico. Donc Stéphane, il est là, non?
Ouais, il est là, on l'a mis. Alors, pour l'instant, il n'a pas de micro et caméra encore, mais il est rentré.
Oh là là. Et on peut tester aussi comment ça s'appelle, la salle pour le jury, là?
Oui, on doit pouvoir la lancer puis la fermer. Donc, je pense qu'on doit pouvoir.
Attends, où est-ce qu'il est zoom?
C'est...
Ouais, c'est Nico. Donc
Ouais.
Stéphane, il est là, non?
Ouais, il est là, on l'a mis.
Allô?
Ah oui, Giovanni.
Tu m'entends, Thibaud?
Oh là là. Et on peut tester aussi comment ça s'appelle, la salle pour le jury, là?
Ouais. Oui, on doit pouvoir la lancer puis la fermer. Donc, je pense qu'on doit pouvoir.
Allô, allô?
Je suis de retour. J'étais tout seul, là.
Tu m'entends, Thibaud?
Oui,
Allô?
Stéphane, mets ton micro.
Bah, il est mis, là.
Ouais, là, tu m'entends. Tu m'entends ou pas?
Tu m'entends ou pas?
Je t'entends, ouais.
J'ai des retours.
Mais est-ce que tu m'entends, toi?
Oui.
Ah, ok, c'est bon. Non, parce que j'ai pas de retour, en fait, sur ma...
T'as une vidéo?
Oui, oui, je vous vois tous les deux.
Ah, bah, est-ce que toi,
Vous
t'as une
voyez?
vidéo?
Ah, si, je peux mettre la vidéo, mais attends. Ouais, c'est bon, tu vois?
Ah, ouais, on te voit, ouais.
Ouais.
Oui, pardon, j'avais des bruits parasites, mais c'était de ma faute.
Ah non, mais j'ai dit c'est Nico.
Ouais,
Je sais plus. Qui a dit c'est Nico?
Normalement, du coup, donc c'est ma sœur qui gère le host, du coup, et
Ouais,
normalement, elle l'a mis dans la salle et elle l'a ouverte. Donc, je sais pas si.
Ouais, j'y suis allé. J'étais tout seul, alors je suis reparti.
Ouais,
Mais
bah.
ça avait l'air.
Ah, mais là, tu es sur Zoom?
Là, je suis sur Zoom.
Ah, moi, je suis sur YouTube, je crois.
Ouais, mais t'as envoyé qui Zoom? Zoom, qui doit aller sur Zoom?
Alors, Zoom, il y a le jury, il y a Coati et il y a des amis et de la famille. Et après, Diana et trois.
Ah, mais c'est Quati, mais pas Nico, on est d'accord.
Non, mais je peux pas aller vers
Nico, j'ai fait en sorte de.
Ouais, il y a un lien Zoom. Ouais.
Il y a un lien Zoom, bah, je peux le renvoyer, je pense. Je ne sais pas si tu as le mail, mais on peut le faire sur le mail.
Ah, c'est bon, il est dans le mail parce que j'ai renvoyé un mail à Coati, il y avait le lien Zoom dedans?
Je sais pas.
Peut-être, attends, je vais voir ça. Tout Coati. Rappel si aujourd'hui est 14h. Zoom, ok. Ouais, non, il y a le lien Zoom, c'est bon. Ouais.
Ok, bon, bah, nickel.
Bon, ça a l'air de marcher, quoi.
Bah, ça a l'air pas trop mal. Hein.
Et attends, ah oui, si on voulait partager, c'est quoi? Si on voulait partager l'écran dans. Je vais peut-être tester de partager l'écran dans le truc de jury, là.
Bah, alors, je sais pas s'il y a celle où.
Ouais, join, ouais. Ok, j'y vais.
Ouais. Et tu peux essayer de partager l'écran.
Ah ouais, d'accord, et tu reviens dans la... D'accord, ah, mais c'est bien. Ok, c'est pas mal.
Ouais, nickel.
Par contre, je vois pas où est-ce qu'on peut régler les trucs view, là, ces différentes présentations.
Ça a marché.
Ah, en haut, tout en haut à droite. Tu peux faire speaker, galerie.
Oui, c'est ça. Soit tu vois celui qui parle, soit tu vois tout le monde, soit...
Ouais, j'imagine ce qui est
Je
speaker.
vais me mettre en speaker view, comme ça je vois celui qui parle.
Galerie d'abord, peut-être et speaker après.
Chat. Ah oui, en fait, je voulais tester le chat.
Il y a tout le monde qui va arriver, hein, Stéphane.
Ouais, to everyone,
pardon.
to Thibaud, to...
Là, c'est ça, il n'y a pas encore vraiment
si
de
je fais Thibaud, direct message.
Je suis pas, du coup, je peux pas le mettre.
Ouais. Il y a Clémence qui arrive.
Bonjour.
Bonjour, tu nous entends, c'est bon?
Vous m'entendez?
On t'entend.
Oui, bonjour.
Ok, impeccable. J'ai plus qu'à mettre la vidéo. Voilà.
Ça va?
Bah ouais, vous.
Moi, ça va, ouais. Ça va, ça va. On était en train de tester que tout marchait bien. Il y a une salle après pour la délibération.
Ouais, j'ai vu, ouais, super.
Donc, ça a l'air de marcher.
Ok.
Les documents et tout, quoi. Nickel. Je pense que c'est bon. Quand tu as fait, t'as pu imprimer les documents, Clémence?
Ah oui, tiens, faut que j'aille les. Oui, j'ai imprimé les PDF au moins. Je vais aller les chercher parce que je ne suis pas dans mon bureau pour foutre la paix à mon co-bureau. Je reviens.
Ok, tout de suite. Ouais, ok. Bon, bah nickel.
Bonjour.
Bonjour.
Ah, c'est Christophe, ça va?
Salut, ça va et toi?
Ouais, ça va, ouais.
Ouais.
Ça va, ouais.
Bon.
Oui, bonjour.
Vous êtes au labo à Nice?
Moi, oui, quoi. Thibaud est chez lui, parce qu'il avait une bonne connexion, meilleure que chez nous.
Ah oui?
Hop, voilà. Et puis, les Word, on verra si on remplit. Enfin...
Salut Clémence.
Bonjour, ça va?
Ça va, ouais. Et toi?
Ça roule.
Ah, tu es au labo, toi aussi, ouais.
Ouais, moi je suis au labo aussi.
Ouais.
Un beau faux plafond. Il est plus beau que le mien.
Ah bah c'est le mien. Moi, je vous bats tous. Hein. Je sais pas
Ah
où
oui,
dans
t'en
l'image,
as même
mais
plus, là.
j'ai des dalles de...
Ah oui, d'accord.
Ouais,
L'INRIA m'oblige à me mettre devant le trou du faux plafond là, pendant la présentation. Donc, oui, je suis pas mal là. Alors, hop là.
Ouais, en fait, on se rend pas compte qu'il fait 1 mètre sur 1 mètre.
Salut Stéphane.
C'est les
En
magies
fait, il fait 2 mètres sur 2 à peu près.
C'est les magies du grand angle, ça.
Ouais, c'est clair.
En fait, c'est un INRIA Potemkin ou en fait, t'es pas à l'INRIA, c'est des faux décors.
Après, Zoom, ça permet de mettre un fond d'écran comme on veut. Donc, tu peux faire semblant d'être au bureau si tu veux.
J'avais essayé, mais il me disait que la machine n'était pas si puissante, je ne sais pas trop quoi.
Ma sœur avait passé sa thèse et après elle demandé aux gens de rallumer. Et j'avais oublié que j'avais mis un fond d'écran avec l'univers derrière. Du coup, j'ai rallumé, je suis arrivé avec l'univers en fond d'écran.
Attends, c'est classe, attends.
Oui, finalement, c'était un thème, elle fait du climat, du coup, c'était bien dans le thème, c'est bien passé, mais sur le coup, ça surprend un peu.
Donc là, c'est chez toi, c'est pas un fond.
Non, là, c'est
vraiment. Ah, c'est bon, tu as trouvé le mur chez toi qui était bien blanc et tout, tranquille.
Précisément, c'est chez ma mère. Du coup,
ouais.
Elle a un bon fond, une bonne connexion, donc c'était parfait. Banco.
Nickel. Hop là. Alors. Hop.
Tu l'as fait en français ou en anglais, Thibaud, la soutenance?
Alors, la présentation sera en anglais parce qu'il y a un membre du jury qui ne parle pas français. Et après, les questions, par contre, du coup, comme vous voulez, ça peut être en français sans souci.
Ah bah, du coup, je vais rester sur l'anglais, moi, s'il y a quelqu'un dans le jury qui ne parle pas français.
Oui, il y a deux. Donc, il y a Augustin Chaintreau qui est aux États-Unis, mais qui a été français.
Qui a priori parle français, ouais.
Il y a Pawel Pralat, par contre, qui est canadien et qui, du coup, parle français.
Ça se prononce Pawel?
Je suis
comme ça qu'on le prononce.
Oui, voilà, c'est ça.
Nico
à l'INRIA.
Oui. Bonjour Clémence et Christophe. C'est Pawel.
Salut. Ok. Oui, parce que je n'ai pas pensé, mais il faut que je regarde les noms pour pas trop massacrer les noms. Ok, je devrais y arriver.
Hop. Encore là. C'était le lien YouTube. Ça marche.
Tu as vérifié le lien, c'est ça?
Tu l'as vérifié? Ouais, non.
Ah, super. Ouais. Ouais, normalement, ça devrait être bon. Alors, j'ai regardé tout à l'heure, ça a l'air bon. On verra.
Ok.
Ouais.
Pour la joie pour pointer les présents sous Zoom. Il nous manque une bonne partie du jury, sauf erreur.
Oui.
Sur le lien Zoom, il y aura le jury, les membres de l'équipe Coati et quelques amis et familles a priori. Et après, il y a un lien YouTube à côté aussi où les gens du coup peuvent se connecter les autres personnes.
D'accord.
Et du coup, du jury, il manque encore quelques personnes.
Oui, il manque Augustin, Jean-Loup et Pawel, donc.
Ouais.
Ouais, Jean-Loup, Pawel. Et Giovanni, ouais. Giovanni.
Ah oui. Je vais pas lire.
Monétisé, ouais, je sais pas si.
Pardon?
Non, Stéphane demandait si la vidéo YouTube était monétisée, mais.
Ah bah ça va faire.
Quand on est en thèse, on a besoin d'un petit soutien financier.
On veut nos 2% de la fortune que tu vas faire. Grâce à ça, quand même.
J'ai prévu quelques placements de produits au début des questions, si ça ne vous dérange pas.
Tu vas faire de la pub pour INRIA?
Quand je vois, je prendrai ma bouteille, super bouteille Vitel.
Ah oui, comme.
Il y a la polémique des bouteilles à l'euro, attends, fais attention.
Ah oui, je n'ai pas suivi. Mais j'avais vu ça, Roland Garros, effectivement, toutes les interviews, ils ont leur bouteille de Perrier ou je ne sais pas quoi.
La session, le début de session, des questions, quoi.
Il faut que je regarde l'heure à ma Rolex pour savoir quand est-ce qu'il faut que tu arrêtes de parler.
Le timing est bon.
Non, c'est cette histoire d'un joueur célèbre là, qui a refusé du Coca-Cola et l'action a perdu.
Ouais, Ronaldo.
Ouais, 4 milliards, ils ont dit.
Ah ouais.
Après, il paraît que ça descendait avant, quoi. Alors, je ne sais pas la vérité ou pas.
Mais est-ce qu'il y a un délit d'initié? Est-ce qu'il a des copains financiers qui avaient.
Après, il y a quelqu'un qui a fait pareil avec Heineken, mais ils n'ont pas dit si Heineken avait perdu des pots. Apparemment, non.
Apparemment, c'est commencé l'Euro. Les Français ont fait 2 matchs nuls, c'est ça? Ou un truc comme ça?
Je crois même qu'ils en ont gagné un, mais non.
Ils ont gagné un victoire de
un but
match
contre son camp de l'Allemagne.
Ah oui, c'est ça, ouais.
Ils ont gagné contre quoi? Le Monténégro ou un truc comme ça?
Non, on a gagné contre le plus fort, normalement, contre l'Allemagne.
Non.
Enfin, les Allemands se sont tirés une balle dans le pied contre nous, du coup.
Oui, ils nous ont
contre nous, ouais.
Alors, au début, ça voulait dire qu'on allait être champion d'Europe. Et puis après, quand l'Allemagne a manqué finir dernière du groupe, les gens ont dit que c'était un bon signe.
Ouais, c'est clair.
Ouais, mais il passe en 8e ou pas alors?
Oui.
Ouais, quand même.
C'est lundi. Sur le lien YouTube de Thibaud. Alors, attendez, le jury.
J'ai l'impression qu'il nous manque toujours Augustin, Jean-Loup, Giovanni.
Tu leur as bien précisé que c'était l'heure de Paris, parce que
oui.
C'est pas mis dans le mail, c'est pas mis.
Jean-Loup, il est à La Rochelle, normalement, il est au courant.
Jean-Loup, il est au-dessus, normalement. Alors, je sais pas si c'est au-dessus, je peux aller voir. Je peux taper au faux plafond, je vais peut-être entendre, mais pas trop fort quand même.
C'est convivial chez vous.
Et oui, non, Pawel Pralat m'avait demandé aussi, du coup, ce sera 8h pour lui, 8h du matin.
Ah oui.
Alors, on a été sympa à 8h, ça va encore. C'est pas le. C'est encore raisonnable. Non, je veux dire, c'est raisonnable. C'est pas.
Ouais, j'ai vu que tu avais une notion d'être sympa, toute relative dans la préparation de cette soutenance.
Oui. Ouais, quand tu as des enfants, 8h, c'est hyper tard, c'est pour ça. S'il n'en a pas, oui, c'est très tôt. D'accord. Alors. Il reste 1 minute et il nous manque 4 membres. Je sais pas.
On n'est pas à 5 minutes près.
Ah, bah, c'est Giovanni, ouais, c'est pas mal, Nico, merci.
Oui, Jean-Loup, Guillaume qui vient d'arriver.
Ok,
Cool.
Super.
Bonjour.
Salut Jean-Loup.
Bonjour.
Ah, lui, il n'est pas au bureau.
Ouais.
Ah non, je suis pas au bureau, je suis à la maison.
Plus beau plafond. De nous.
Bon, c'est une comparaison de nos faux plafonds avant que tu arrives.
Ok. Toi, tu as des trucs bizarres suspendus, Clem.
Ben, c'est ça, je leur ai fait un petit panoramique pour leur montrer à quoi ça ressemblait.
Ok. Ah, il y a Pawel qui est en train de
Pawel se
connecter.
connecte. Ouais.
Hello, Pawel. Can you hear us?
Oh yeah, hello.
Oh,
Hello.
Yeah, hello. So we are waiting for 2 members of the jury. So,
I think Augustin and Giovanni.
Giovanni. So.
So everything at Ryerson for some reason starts 10 after. So I don't know. I think I got mixed up, but I think, yeah, it's 8:01, so I'm not late. So.
No, you're perfect. Perfect timing. Thanks a lot. Giovanni.
Hi, everyone.
Hey, hello, Giovanni.
Hello.
Hello.
How are you?
Fine, fine.
Yeah, perfect. So I guess Augustin.
Yeah.
I don't know if you remember, but Augustin told us that today he had this his child, his 4-year-old child, and he was alone. So probably it would be a little bit difficult for him to follow, but he will do his best. But so maybe I explain.
Yes, maybe, but I would prefer if he would at least be connected.
Yeah.
So if you agree, I think we'll leave him 5 more minutes or so to.
Sure. I will send you an email.
Hello.
Hello.
Hello, Augustin.
Hello, Augustin.
How are you?
Hi, everyone.
Fine, and you?
Bonjour, Augustin.
Bonjour.
Okay.
How are you? Nice to see you.
Okay, so whenever you want, we can launch the. Shall I start now, or do you want to wait a bit more?
Well, I think we can start now. What do you think, Thibaud?
Yeah, maybe before to start, I might just remind you that I will do the presentation via Zoom and then the question, and then for the deliberations there will be a room that you will be able to join after the question. So you will probably have a message and you will be able to join it, and then to leave it when you're done. So yeah, just remind you.
Okay, thank you. So hello everyone. So we will hear today the defense of Thibaud Trolliet. The committee is constituted of Augustin Chaintreau, Christophe Crespelle, Frédéric Giroire, Jean-Loup Guillaume, Giovanni Neglia, Pawel Pralat, and I'm Clémence Magnien. So Thibaud, you have approximately 45 minutes to present your work, and then we will have a round of questions before the jury deliberates. So,
okay, perfect.
The floor is yours.
Thank you. I will share my screen so you will see the slide.
Perfect.
Okay, perfect. Do you see well my slide? Is it okay?
Yes, it's perfect.
Okay,
Yes.
perfect.
Yeah, that works.
Thank you. Okay, then let's start the presentation. So thank you very much for being here today. So today we will talk about the study of the properties and modeling of complex social networks. And before to start the presentation, I just would like to deeply thank Frédéric Giroire, my supervisor, for his presence during all those years, and also everyone from the jury members that have accepted to be part of my PhD committee. So thank you very much. And so now let's go to the presentation. So I will first start with the motivation of the PhD, why I think it's an interesting subject to study. And then I will present one of the main contributions of my manuscript, which is a new random growth model, which is able to build any graph with any real or theoretical degree distribution. And then I will briefly present the interest clustering coefficient before to conclude. So let's start with the motivation. So first of all, here at the bottom right, you will find my PhD subject. And you see that we will talk about complex social networks. So I think it's important to define what this is. So a network is defined as a group or system of interconnected people or things. And we say it's complex if it has some non-trivial topological features in it. And so we see that the definition of a network is really broad. It really encompasses a lot of phenomena. And so we can, for instance, think about social networks, bank transfer, but also roads, food chains, or ADN interactions, or neurons, and so on and so on. And so today we will focus about one specific network, which is the online social networks. So I guess everyone have heard about it, and the name is quite transparent. So it's, for instance, we think often about Facebook, Twitter, but also YouTube, and so on. And I guess it won't be a really big surprise also if I tell you that it has acquired a huge influence on nowadays society. But maybe just to give a few numbers that might enlighten those facts. For instance, we have 1.8 billion daily active users on Facebook and around 150 million on Twitter. The daily time spent of them is of around 2.5 hours. And finally, we have around 1/3 of UK and France populations that use it as a source of information. So for this reason, I think it's really important to study them, but I just also wanted to add two more reasons that I think are really interesting. The first one is that it's been a long time since people wanted to study social interactions. And I think it's the first time in history that we have access to such huge data sets of social interactions. And the second one is that the online social network really appears fast in society. And it came with some advantages, of course, but also with multiple drawbacks that we just begin to apprehend. And so we can think, for instance, about fake news, about bots, and also about polarization, and so on. So for all those reasons, it's important to study online social network, but it's also hard to do so. And the two main reasons are that, first of all, online social networks are often they often belong to private companies. And so as researchers, we only have access to limited public API, and so just a part of the network. And the second reason is for ethical reason, because if you want to study the network, you can't always study it directly. For instance, let's suppose you study fake news. You can't really put a fake news in the network, let it propagate, let people believe it, and say it's okay. So for all those reasons, we will want to have some synthetic networks. And this is what models will enable us to do and to circumvent this problem. So let's talk a little bit about models. So first of all, I just wanted to remind that we have those real-world networks, and mathematicians use what we call graphs to represent them in the mathematical world. And so what is a model? A model is just a simplified representation of the world through a few mathematical rules, which are supposed to approximate the real-world laws. And so the idea is that we will want to have some models that will build synthetic networks, and we will hope that those synthetic networks will be close enough to the real-world network, such that we can study those synthetic networks and these synthetic graphs and what happened in them, and say, okay, we suppose they are close enough, so if this is what happened in synthetic networks, it will happen more or less the same in real-world networks. And so to do so, we need to have some models that looks like real-world networks. And so models aim to capture the network's properties. So we have to define now exactly what are the properties we want the models to recover, what are those network's properties. And so we have two, I think we can separate them in two parts. The first one, which is, I think, the most interesting one, is that if you took some networks from various domains, either social networks or banks or ADN interaction and so on, you will find some common properties, even if it's from various domains. And so, for instance, we will find the presence of communities, as we can see here, but also a power law degree distribution, high clustering coefficient, and so on. So we will come back later on those terms. And on the other part, we also have some specific properties to the networks, and that might be either due to the graph specificities, so it can be a directed network, hypergraph, and so on, but also due to network specificities. And for instance, later we will see an example where the policy of Twitter lead to some really specificities to this network. So we will come back later in the presentation to this point. And so models want to find those properties. And so just to talk a little bit about the related work. So here we have a bunch of classical models. And here on the column, we have some properties that we like to classically study. So the degree distribution, the clustering coefficient, the distance, and the modularity. And I think what is interesting to see in this table, if I just put some colors in it, is that we can see that there is still a lot of work to do. So here, for instance, for the question mark, we have the cases in which I didn't find any theoretical study about them. But more interesting, I think, is that we can see that for directed and hypergraph, we also have a lot of work to do. And one of the reasons for that is that the metric we introduce are often for undirected networks. And so the first thing to do is first to define them for directed and hypergraph, and then to study them in the model. And so here there is still a lot of work to do. And another point I wanted to highlight here is that we can see that for the degree distribution, there is a lot of work that has been done. So we see that all of the cases have been fulfilled. But it's often with the same thing. We see that it's often what we call power law, I to the power minus something, I to the power minus something, and so on. And so there is also some work to do here for random graphs in order to enlarge this and to find some other degree distributions. And so about my contribution, the first one is to enlarge those degree distribution. So this is what I will mainly present today. And there is also, so yeah, this is the first one. And there is also here a contribution about the clustering coefficient for directed networks. So this is the interest clustering coefficient that I will present also today. And we also have a model for hypergraph with modularity, so on this place. And finally, with a new tool, we managed to compute the jointed degree distribution for the Bolobas and all model. So this is for this case. So we will come back about it later. So just to summarize the contribution of the PhD, concerning the model, I introduced...
Are we asking clarifying question now or later? What's best?
I think it's later, but maybe...
Okay, sure, no problem.
Yeah, usually questions are for after the presentation, unless there's some really...
Oh, yeah, it was just a clarification on the table. It was very quick. What is this A1 for spatial PA? Is it just a parameter, or does it have a meaning? Because the other are pretty...
Where, sorry?
Oh, if you look at spatial PA in the degree distribution, you have 1 + 1 over PA1, and I'm not sure what A1 stands for.
Yes, sorry. So A1 is a parameter of the spatial potential attachment.
Okay.
So it's one of its parameters. I didn't develop it, but it's a parameter of the model. Just like here we have P and alpha.
Okay.
Parameters of the model.
Okay, so just like the other parameter. Thanks.
Yeah. No problem.
Thanks.
So about the contribution, so about the new model, there is a few of them. So the first one is to build graphs with any wanted degree distribution. And there is also a model to build hypergraphs with power law degree distributions and more importantly with communities. And finally, I also introduced two models to build graphs with Twitter specificities. And about the tools, there is this interest clustering coefficient, which is a new clustering coefficient for directed graphs with interest links. And finally, this Monte Carlo framework, which is a tool based on Markov chains, which enables the computation of degree distribution of a bunch of preferential attachment models, and especially ones with more than one dimension, like directed ones or even more complicated ones. And so here, of course, today I won't have the time to go through all of this, so I will just focus on the wedge ones, the one to build graphs with any wanted degree distribution, and the interest clustering coefficient. And just before to do that, I just wanted to introduce you the real-world network I have worked on during my manuscript. So there were two main ones. The first one is a Twitter snapshot that have been crawled by Maxime Gabiakov and Arnaud Legout in 2012. And so it's a directed graph of followers, which means that each account of Twitter will be a node of the graph, and we will put a link between A to B if the account A follows the account B. And if you do so for every account, you end up with a graph with 500 million of nodes and 23 billion of edges. So it's a really huge network. Actually, it's the biggest directed online social network available nowadays to what we know. And the second one is a co-publication hypergraph that has been extracted from Scopus database. And here, every node will be an author of a scientific paper, and a hyperedge will be, we have a hyperedge between a set of nodes if they have published a paper together. And so here we have 2.2 million of nodes and 3.9 billion of hyperedges. And so here for Twitter, I studied the degree distribution, the clustering coefficient, and the correlations between degrees. And I insist here on the S because since it's directed, there is a different degree distribution and clustering coefficient. And for the co-publication graph, I studied the degree distribution, the presence of communities, and the publications between those communities. And finally, I also studied some other smaller data set for the clustering coefficient. And so here again, today I will just focus on what will be useful for the model and the interest clustering coefficient. So this is the degree distribution and the clustering coefficient of Twitter. So that's it for the motivation. Now let's go to the main interest of the presentation. So I will present now this random growth model for any real or theoretical degree distribution. So, as we have seen in the introduction, most of real-world networks share common properties. So, power law degree distribution, high clustering coefficient, and so on and so on. And here we will focus on the degree distribution. And so, what does it mean that degree distribution follow a power law? It means that it follows something like that. So, it's in I to the power minus alpha. And in practice, alpha is often observed between 2 and 3. So we talk about scale-free structure in that case. And qualitatively, the idea behind that is that we have nodes with really high degree. So we have kind of celebrities. So in social network, it's really celebrities, but we can think about the same idea for added interaction and so on. And so since a lot of networks follow power law degree distributions, models have mainly focused in building graphs which will recover these power law degree distributions. But actually, there is also a lot of degree distributions that are not power law. So for instance, here I just gathered here 8 degree distributions that I extracted from different seminal papers from various domains, so biology, online market, and so on. And what I didn't tell you is that if you plot power law degree distribution in a log scale, then you will find a straight line. And here we can definitely see that we don't have straight lines, so that's not power law degree distribution. So we have here what we will call a broken power law, maybe, which means that we have a straight line and then after a point another straight line. So here, here, and also here. Sometimes we have some really faster decrease, so maybe exponential or so on. And sometimes we have some really unusual shapes, so which are probably due to the network itself. And just to give another example, there is this really interesting work by Brodo and Claude from 2 years ago, where they took over nearly 100 networks from various domains, and they studied the degree distributions to see if it was Pawel or not. And they have found that fewer than 36 networks, so around 4%, exhibit the strongest level of evidence for scale-free structures. So for this is degree distribution, Pawel law with exponent between 2 and 3. And so we see that actually when you have a model for Pawel law, all those networks can't fit in those models. So, of course, in the related work, there had been a bunch of other models for other degree distribution. So, as we have discussed, there is a lot for Pawel degree distributions, but there is also some for stretch exponential distribution. So, for instance, it's when you take a preferential attachment in I to the power alpha with alpha smaller than 1, and also some with exponential cutoff distribution. So, for instance, when you choose some node deactivations, and so on. And actually, our first goal when we introduced our first goal was just to find a model that would be able to build graphs with broken Pawel law. But we managed to do way more than that because we here propose a new random growth model, which is able to generate graphs with any wanted given degree distribution. So what is this model? Let me introduce it. So it's based on the Jean-Loup model, and it's a random growth model, which means that the idea of a random growth model is that at each time step, you will add nodes and or edges, and you will connect those edges to existing nodes, depending on some rules that will depend on the model. And so in our case, we will start with an initial graph G0, and at each time step t, we will have two possibilities. Either with the probability p, we will add a node u and an edge attached to this node, and that we will attach to an existing node v. And this node v will be chosen as a function of its degree, so proportionally as a function of its degree, and this is just a normalization term. And with probability 1 minus p, then we will add an edge between two existing nodes, and those nodes will be chosen proportionally of their degree. And so the main difference between what is usually done is that usually we pick nodes randomly proportionally to their degree. And if we do so, we know that it will give a Pawel law in most cases. And sometimes, for instance, we have seen if we choose not proportionally to its degree, but the degree power something that is smaller than 1, then we find a stretch exponential and so on. But here we generalize it by saying, okay, here now we have this attachment function, which is a parameter of our model. And we say that, okay, if we manage to link this attachment function with the degree distribution you want, then you can find any degree distribution you want by choosing correctly this attachment function. So now we just have to link this attachment function with the degree distribution. And this is what this really nice theorem gives us. It says that, so let P be a probability distribution of mean mu and satisfying this condition, so this has to be bounded. Then in the proposed model, so just to remind you that in the proposed model, we have two parameters, the parameter P and the parameter F. So in this proposed model, if P is chosen as 1 divided by mu, and if the attachment function is chosen according to this formula, then the degree distribution of the created graph will be distributed according to P. And so that means that if you want a probability distribution, you just have to compute your attachment function using this formula, put it in the model, and you know that the synthetic graph you will have this degree distribution P. So, of course, I won't go through all the proof here of the theorem, but I just wanted to show you the main trick, the main creative thing of the theorem, of the proof to find this formula. So here I will call n of it the number of nodes with degree I at time t. N of t will be the number of nodes at time t, and p of I is the limit of the fraction of both of them. So we have a direct link between n of p. And here I will just present the idea of the recurrence equation, which is quite similar in a lot of random growth models. And the idea is that we can find a recurrence equation between the number of nodes. I have lost my mouse, sorry. Oh no, okay, sorry. Yeah, so the idea is just, okay, we are wondering ourselves at time t plus 1, what are the number of nodes of degree I? Well, we know that it will be more or less the same at the number of degree I at time t, because what might happen between these two time steps? Well, we know that we will add node and or edges, and when we add edges, we can connect to new nodes, and if we connect to a node of degree I minus 1, then he will go to degree I, and so we will increase the number of nodes of degree I. And on the contrary, if we connect to a node of degree I, then it will go to degree I plus 1, and so then we will lose it as a node of degree I. And that's more or less what can happen. And so we know that the number of nodes of degree I at time t plus 1 is what we had before, plus a particular case if I is equal to 1, and plus a term that is the probability that we connect to a node of degree I minus 1, and minus the probability that we connect to a node that is of degree I. And knowing this recurrence equation, so now just remind me that I just put the recurrence equation in this box, so this is just the same thing that we had before, trust me on this. And what we can say is that, okay, if we suppose we know the attachment function, then we have a recurrence equation between I minus 1 and I for n, and we can iterate this recurrence equation in order to find this formula. So this is some classical formula, and especially when the attachment function is linear, this gives a power law. So this is how you classically show that you have a power law. But what is interesting is that we can also see that we have here a recurrence equation also on the attachment function. And if now we suppose that we know this n of I and n of I minus 1, then we can reverse the recurrence equation and iterate over this attachment function. And this is how we obtain the formula of the theorem. So yeah, that was the main idea, to reverse this recurrence equation over the attachment function. So of course, the proof has some more technical difficulties, but I won't go into them. Now that we have this main idea, we can go with the application. Yeah, sorry. So just to go about the applications, here we computed the attachment function for a bunch of theoretical degree distribution. And for instance, if you look at the Jean-Loup distribution, so I told you it was a power law. It's not exactly true. It's more a fraction of gamma function, but it's more or less the same thing. And we see that we find an attachment function that is linear, which makes sense because we know that if we take an attachment function which is linear, then we will be in the classical Jean-Loup model, and so we have a power law. So it's what was expected. We also computed it for the exact power law and geometric law, and for the broken power law. And I just want to spend a little bit more time on the broken power law, because as I've told you, our main goal was to have a model that would be able to build a network with a broken power law. And the idea behind that is because I personally believe that a lot of online social networks have actually a degree distribution is broken power law instead of power law. And so here we have the broken power law. So just to remind you, it's when you have a power law with a given exponent until a given value d, and then you have another power law after this value d. And here is the attachment function we obtain. So we see that after the growth here that has been chosen to 100, we have a linear attachment function. So this was expected because we know that for a power law, we have a linear attachment function. But what is more surprising is before that, we see that we have some unusual shape, and especially the attachment function can even decrease, which is quite unusual. So we keep for further work the study of this attachment function, but it would be interesting to understand how it evolved. And just to check that everything was okay, we took this attachment function and we put it in the model and build a random graph. And this is the degree distribution we obtained with that random graph. And we see that it indeed is a broken power law with a block around 100. So it was expected, but yeah, everything is fine, which is reassuring. And so last but not least, there is another application to our model, which is that actually the formula we have in the theorem can also be applied for real-world degree distribution, for practical degree distribution. And I think it's an interesting application because, so let's see the case of Twitter. We wanted to apply it to the Twitter graph. So as we have seen, the Twitter graph is directed, so we had to take an undirected version of it. And to do so, I just took each arc and made them undirected. And this is the degree distribution we obtained. And what we can see here is that, well, at the end, it might be a power law because it's a straight line. But before that, it's definitively not. And especially around 20 and around 2000, we have some unusual spikes. And actually, we can explain them, and especially this one, because it's due to a Twitter policy which says, okay, we have two more, we have bots in our networks, and so we want to avoid them. And to avoid them, we'll just put a rule that says, okay, if you want to follow more than 2,000 people, then you're a bot, and so you can follow more than 2,000 people. So actually, there is some special case you can. If you're a celebrity, that's okay, but otherwise you can't. And that explains this huge spike because we have a lot of accounts that are with 2,000 followers or almost 2,000. And what is interesting here is that if now I want to build a random graph that will look like Twitter, for sure I won't find a model in the literature that will build me something like this and with these spikes. And if I would like a model with that, I will have to introduce this specificity in my model to say, okay, at 2,000, do that special case. And with our model, we are able to treat this case because we just have to say, okay, give us this degree distribution, and no problem, we will build random graphs from it. And so, of course, that's what we have done. So this is the degree distribution I have just shown you. And we computed the attachment function from this degree distribution. So this time, it's a practical one. We see that we have here some decreasing spike around 20 and 2000. This might be understood just by hand by the idea that if we remind correctly, this attachment function is the probability in the model to receive new edges. And since we want a lot of nodes with degree 2000, when in the model a node arrives with degree 2000, then we don't want it to receive new edges. We want it to stay to 2000. And so this is why the attachment function decreases. And after that, we put the attachment function in the model. And this is the degree distribution we obtain from this model. So be careful that the number of nodes is quite smaller because of this huge number. But still, we see that the degree distribution, we find the spike around 200, around 20 and around 2000. Yeah, so that's it for what I wanted to present you. So just to conclude and to talk a little bit about the further work about this model. So just to summarize the contribution, we had the introduction of a new model which is able to generate graphs with any given degree distribution, either theoretical or extracted from real world. We also computed the attachment function for some theoretical distributions. And finally, we made a study on a real-world network, which is a Twitter network. And about the further work, so the first one would be to expand the model to a directed one, because as we have seen, Twitter is directed, so it might be good to have a directed version of it. But I think it shouldn't be a big problem. But more importantly, I think that the relation we have found in the theorem between the attachment function and the probability distribution is really simple. So I just remind it here. It's in another form, but it's the same that what we had in the theorem. And we see that it's really simple. And thus, I hope it could enlighten some general links between the attachment function and the distribution. And for instance, if you have looked at the manuscript, you might have seen that we have been able to show this really nice theorem, which says that in the model I have presented, if f tends to the infinity, then the degree distribution will be heavy-tailed. And on the contrary, if f is bounded from above, then P will not be heavy-tailed. And this is really interesting because the heavy-tail property of the network is something that has been really studied and questioned. And here we see that in our model, it really only depends on something simple, which is, will the attachment functions tend to the infinity or not? So, of course, be careful that this is true only in the model I have presented, but I believe it can be enlarged to other classical models without difficulties. The proof will probably be more or less the same. And I also hope that this might enlighten general links in real-world networks. And so maybe by looking at the degree distribution, we might understand how people tend to attach to each other. Yeah, so that's it for the new model I wanted to present you. So now I will go with the second part of the presentation, which is the interest clustering coefficient. So I will go, of course, quite faster than on this part, but it's just to present you the idea what is interest clustering coefficient. And so what led us to this question? Yeah, sorry. So first of all, as we have seen, so I just come back to this slide. So most of real-world networks share common properties. So probability distribution and so on. And here we will focus on the clustering coefficient. And the question we were asking ourselves is, okay, we wanted to study the clustering coefficient in the Twitter snapshot we had. So first, let me remind you what the clustering coefficient is, what is its classical definition. The idea behind the clustering coefficient is that the friends of my friends tends to be my friends. And so the idea, if we look at it here, is that we will ask ourselves, what is the probability for this link to be here? And so if this is an account, this account will have a friend which will have a friend, and we will ask ourselves, will he also be my friend or not? And so the definition introduced by Barra and White of 2000 of the global clustering coefficient is just 3 times the number of closed triangles in the graph divided by the number of connected triplets of vertices in the graph, so what we call an open triangle. And this factor 3 is just here because we have 3 open triangles in a closed triangle. So that's a nice definition, but as we have seen, Twitter is directed, and so this is an undirected definition, so we have to find a directed definition of this clustering. And the first idea we might have would just be to put direction in the links, and actually that's what Fagiolo did in 2007, so he proposed a new definition for clustering coefficient, which is directed, and he just put direction in the edges. So there is different ways to do that. Here we will focus on 2 of them, what we call the transitive directed triangles, which is if A follow B and B follow C, what is the probability that A also follows C? And the cyclic directed clustering coefficient, which is if A follow B and B follow C, what is the probability that C also follow A? So now that definition is directed, but it's still based on triangles, so more or less the friend of the friend. And it is known since 2014 that Twitter is both an interest and social networks. So that means that there is some social link in the networks, but there is also some links where you will follow someone just because he is a celebrity or he is a source of information and you want information from it. And this is why we wanted to introduce clustering coefficients that would capture this interest part of the network. And it led us to the interest clustering coefficient. So the idea behind it is that if we share a common interest with someone, then we are more likely to share another common interest. And if we look at the right figure here, so here we would have two accounts of the network, and they will have a common interest here. They will both follow this account. And we see that the second one also follows another account. And the question we're asking is, what is the probability that this account also follows this account? And so the definition of the interest clustering coefficient is just 4 times the number of K22s divided by the number of open K22s, where a K22 is this butterfly, and an open K22 is a K22 with a missing link. And here again, we have this 4 just to have a probability between 0 and 1, since we have a 4 open K22 in a K22. Yeah, so that's the definition. And then, of course, we wanted to study it, as I said, in the Twitter network. But we mind that this Twitter network is really huge, so we had to find some really efficient algorithm, because since we are working on quadruplet of nodes, the naive method with just being big O and n to the power 4, if you just take all quadruplets, and of course it would be impossible in this network. And so we managed to compute an exact algorithm which has a complexity in big O of n, where n is the number of edges plus the square of the degrees. So it's around 10 to the power 14 iterations, which is to compare to the 10 to the power 10 edges, so not that much. And we also developed 2 approximate algorithms to compute it way faster, not exactly, but faster. And those methods are with edge sampling and with Monte Carlo algorithm. And so here, so we computed all of them in the Twitter snapshot. And here I will present the results we have obtained with the exact algorithm. So now, what are the clustering coefficients in the Twitter snapshot? So here we have the ICC, so the interest clustering coefficient, the one we have introduced. And here in blue, you have the one based on triangles, so the one introduced by Fabio. And we can see that those 3 numbers are quite high, quite similar of what we could find in other networks, and quite higher than what we could find is in a random graph, for instance, a Ernst 3D graph. We see that the ICC is a little bit higher, but not that much. And the next step we wanted to take is, okay, we wanted to separate in Twitter the interest part and the social part on the network. And the supposition we have made is that the social part might be mainly contained in bidirectional links. So what we call a bidirectional link is when we have 2 nodes and one node follow another node, and this node also follow it back. And the idea is that if I am friends with someone, then I will follow him and he will probably follow me back. But if I follow someone, if I follow a celebrity for information, then maybe he won't follow me back because he doesn't know me. And so we removed those bidirectional links from the network and we recomputed the clustering coefficient without those bidirectional links. And what we obtain is the following results. And so we see that the interest clustering coefficient stay more or less the same, while the clustering coefficient based on the triangles significantly decrease. So it comforts us in this idea that, that the interest clustering coefficient is more for interest links. And so finally, we applied this interest clustering coefficient in 2 applications. The first one is the presentation of a model which is able to recover a high clustering coefficient. And the second one is a new recommendation system, which would be based on interest clustering coefficient instead of triangles. Okay, so that's it for what I wanted to present to you today. So let's go to the conclusion and then to the further work that might be interesting. First of all, I would like to remind you that what I have presented today is just a part of what you can find in the manuscript, of course. So it's the point that we have here in red. But concerning the model, so there is the one I have presented you, but there is also this model to build hypergraphs with Pawel distribution and communities. And there is also 2 other models to build graphs with Twitter specificities. So one to have a high interest clustering coefficient, and one to recover a huge number of bidirectional links. Concerning the tools, there is this interest clustering coefficient, but there is also this Monte Carlo framework, which is a new tool to compute more rigorously and more easily the degree distribution of a bunch of preferential attachment models, either classical ones, but also more complicated ones, and especially ones with more than 1 dimension. So for directed models and more complicated ones. And finally, concerning the experiments on social networks, there is the one I have presented on Twitter, but there is also the one I have conducted in these co-publication hypergraphs and other smaller data sets for the clustering coefficients. And so just to put this contribution, and especially the one of the model in the table we have seen at the beginning. So here in white, we have the table I have presented in the introduction. And in blue, this is the three models I have introduced in the manuscript. So the first one is the one I have deeply discussed today. And we see that the main interest was to have a random growth model that would be able to build the distribution that is really general instead of the classical Pawel we find. And there is also this model for directed graphs, which is able to find a high interest clustering coefficient. So here we are on this case. And finally, there is this model with communities that is for hypergraphs, and for which we found a lower bound on the modularity to show that we have some distinct communities. And finally, about the contribution, there is also this case. So it's not about the model, but it's about the Monte Carlo framework based on the Markov chains, and which this framework we were able to compute the jointed degree distribution of the Bolobas and Hall model, which means it's the degree distribution for it's the number of nodes that have an in degree I and an out degree O at the same time. And it's to what we know the first time that it has been done in the literature. So that's what I have done during my manuscript, but of course during my PhD. But of course there is still a lot of work to do. If you look here, we see that we have still a lot of question mark. But here we see that there is also a lot of open problems for directed networks and hypergraphs, and a lot of cases to fulfill. And as I have discussed in the introduction, one of the reasons is that, first of all, the matrix has to be general, to be generalized, to be transferred for directed and hypergraph. And so one thing we are actually working on is on those two cases is to study the clustering coefficient in random directed graphs models. So that's the first further work, but there is also another one I wanted to discuss with you. Is that all those models actually take in account some parameters, but each time those parameters are fixed at the beginning. So this is some constant parameters, and then we look at the properties for t which goes to the infinity. And the question we have now is, what would happen if we had some sudden change in the parameters during the beginning of a graph? And the idea behind that, what led us to this question, is that we wanted to model the receiving of grants in research. And to model that, one idea would be to have some nodes that would be receiving those grants at some random times. And another idea would be, so I didn't talk during this presentation about the model for hypergraph with communities, but for the ones that have looked in the manuscript, you can have seen that there is this probability matrix P, where each case is more or less the probability for two communities to interact with each other. So in research, it would be for two communities to publish with each other. And the idea would be to change this probability matrix P at some time to represent the change of pluridisciplinarity that might happen when you receive a grant that is supposed to increase pluridisciplinarity. Yeah, so that's it for this. And finally, just to talk about briefly about the publication. So I had two publications that have been accepted to international conference, to the Complex Network Conference. And I have two actually submitted to international conference and two to international journals, one of them being in second revision process. So yeah, so finger crossed for all of them. And finally, I had 3 papers accepted to national conference, so to the Algotel conference. And that's it for what I wanted to present you today. So thank you very much for your attention. And of course, I will be really happy to discuss with you about any point you might have or any question you might have on what is during this presentation or my manuscript. So thank you.
Okay, thank you, Thibaud. So we will now proceed with the questions. So each member of the jury will ask one round of questions, and then we will meet together to discuss the outcome of this PhD. So the reviewers of the PhD will start first. So there's the tradition that the member of the jury that comes from the furthest speaks first. So nobody came actually to your place, but Jean-Loup Guillaume is the one that is geographically the farther from you. So Jean-Loup, you have the floor for the questions. Okay,
thank you, Clémence. Thank you, Thibaud, for your presentation. So I really liked it. Well, I said in my report that you made some very technical contributions, but during your presentation you managed to present everything in a very simple way, giving some sketches, some clear intuitions. So I think this is a good job for this. It's not always so easy to present very technical results in a very clear way. So the main thing that I wanted to say is that you've proposed several models during your thesis. And in particular, I really liked the gross model that you've introduced that allows to reach any given degree distribution and to find the function to put inside to obtain what you want. So I found that the way it is built is very elegant. And you have both theoretical and practical results on this model, so I really liked it. So maybe for my first question, if you could come back to slide 22, please. So you have a bound on this slide for the function g on top of the slide. I would like you to try to give some maybe some simple explanation on this bound. What is the idea behind, and what are the consequences on the distribution that can be used in your model?
Yeah, that's a good question, of course, and I was quite embarrassed with this bound because it looks quite complicated while it's not that much. But okay, so maybe I can first explain where it comes from, and then I will explain what are the implications. But the idea behind this bound in the proof is just about concentration, because when you do the proof, you often work about the mean of the number of nodes, and then you say, okay, you are concentrated, and to use the concentration inequalities, you need to say that at each time step, you can have too much things that happens, and more precisely, it means that actually the number of the change in the attachment function won't be too much. And if you look at that, actually, you can remind that this is f of I plus 1, and this is f of I. So actually, the bound in the proof is f of I plus 1 minus f of I. And the idea is that you won't allow that the attachment function is too high in one time step. Because in one time step, you know that you will only change at the maximum f of I plus 1 minus f of I. And so this is where this bound comes from. And I tried a lot to prove it because my intuition, so I'm not that sure about it right now, but my intuition was that actually it should be true for more or less every probability function that would lead to interesting graphs. And the idea is that one of the limit case is if you take f which is linear, then you will have f of I plus 1 minus f that is a constant. So for instance, it will give y plus 1 minus I, and so it will give 1, or at least a constant. And so it will be bounded, but not decreasing to 0 and so on. So it's more or less a bounded case. And if you take I to the power alpha with alpha bigger than 1, strictly bigger than 1, then in this case, you won't be bounded. So one case where this is not true is when you take I to the power alpha with alpha bigger than 1. But we also know, it's also known that if you took this f, then, I mean, if you come back in this model and you choose an f which is to the I to the power alpha bigger than 1, then you know that you will obtain a graph which will have only one main node that will gather all the edges, and all the other nodes will have only a constant number of edges. So it's not a really interesting graph, and it's not, I mean, it's not, let's say, nice probability distribution, while nice will have to be defined. And so that's why I saw that it would be true for a lot of probability distribution, but I did not manage to prove it. I hope.
Okay, so yeah, sure. So this is kind of related to the. So you've shown some curves on Twitter, maybe a few slides later, and you showed this spike around 20 and I don't know, a few hundred. So this is related to this. So for instance, if you had a big spike on this, maybe the property wouldn't be fulfilled. That's it?
Yeah, that would be true. Actually, if we stay on the theoretical function you might put, if you stay on the theoretical function, you can always have some spike at some point. It's not a problem because you just take the max. I mean, the problem would be in the infinity, and since you're looking at the infinity, it will always be bounded, so that would be okay. So in the theoretical thing, the problem would be to have something that is convex, I think, or concave. I always remember, but I think it's convex. But indeed here, it's a little bit more tricky for practical things because, we can't really go to the infinity, but so, if this was a theoretical bound, that would be okay to have some spike like that because you will bound it at the infinity. So it's more like the attachment function has to be convex. That would be the problem. If the attachment function is not convex, that's okay.
Okay. So I had another question on your models. So you've proposed different models, and one of them. So in your thesis, it was in chapter 5.3. So this is a model with many parameters. So you have, I don't remember, maybe 5 or 6 different parameters in your model. So it's page 90 in the manuscript.
90.
So it's a model H of H0, Px, Y, M, and gamma. Okay, so this is it. So I guess you see where I'm going. So you have many parameters. So you know the Occam-Razor principle that says that let's say that you shouldn't introduce too many parameters unless it's really needed. So what do you think? So of course you want to propose a generic model. So you want it to be as generic as possible. So you need to introduce many parameters to get this genericity. But my question is, how far shall we go in trying to obtain a generic model with more and more properties, or on the contrary, maybe staying on maybe more simple models, but with less parameters? So where is the threshold on this? What's your take on this?
Yeah, that's a good question, and I'm not sure there is a clear answer. I guess it depends on what you want to do for the applications, because indeed there is always, as you said, this threshold where, I mean, the most realistic model would be to just have exactly the edge at the same place and so on. But so then you lose the idea of a model. And the really simple one is where you do everything randomly, but then you're quite far of what you want. And so, I guess the threshold depends on the application you want. If you want something which is really close to, I mean, really, which look like really or not. And I also guess that the best will have, the best thing would be to have models that doesn't explicitly come with those things. So it's also why I like the thing with the attachment function, or for instance for power laws, because you just say, okay, I attach linearly, and then you say, incredible, it's a power law. So I think that would be nice to have some things like that. But yeah, for this model, I guess, so indeed there is a lot of parameters, but you can still simplify it by taking some parameters to 0, and that way to find some simplest models that will have a lot of smaller parameters. So I guess it's okay to introduce a really complicated model as if you can really simplify it and go back to something really simple. And for instance, you can see, so I guess it's okay. Here you have some example when we see we cover some classical models. So you just have to take PV equals 0, PV equal 1, PV equal 0, V equal 1, VT equal 2. So you just fix some parameters, and so they, let's say, doesn't exist anymore, and you find a classical model. Yeah.
Okay. Maybe a last question on the second part of your presentation about interest clustering coefficient. So it's quite similar or really similar to what has been done on bipartite networks. In particular, the global clustering coefficient for bipartite network has the same definition as the one you used, except for the orientation. So what's your view on this? Do you think that we need to maybe use what has been done on bipartite network and try to adapt it to classical networks? Or do you think that we should try to define some properties that are different? In particular, people have worked quite extensively for recommendation and link prediction purposes on stuff like this. So what do you think about this? I don't know if there is really a question in my question, but
no, I think I can answer the question or the question. I understood the question. I think. Yeah, indeed. But to be honest, when we defined this interest clustering coefficient and so on, and we didn't think about the bipartite networks, and we saw about it a little bit too late for my PhD. But indeed, we have seen that it's quite similar. The main difference is that for directed graphs, of course, nodes. I mean, for bipartite graph, you really have two sides. For directed graph, you have. I mean, one node has an in degree and an out degree, but you might say that you can still define it as a bipartite graph by putting all the in degree in one side and the out degree on the other side. In that case, we have 2 times more nodes, so way more nodes, but the number of edges won't change. So that might be used, but yeah, so I guess the main difference is that for directed nodes, you have nodes can have both together. And to answer your question about recommendation, indeed, what we have done for recommendation here was really some preliminary work. So indeed, it might recover with some bipartite recommendation. I didn't think, maybe one point, but I didn't think about it. I don't know if we could do the same thing that we have done for bipartite works, because here we used ICC, and so we really need the in degree and the out degree, and maybe the fact to separate them might change that, but I'm not sure yet. This would have been to think. Yeah, since recommendation was really an application we made quite fast, we didn't saw a lot about it. I don't know if it really answers the question. That.
Yeah, sure. Yeah. Okay, so Clémence, I will give you the floor back.
Thank you, Jean-Loup. So now we will hear the questions from the other reviewers. So Christophe.
Okay, thank you, Clémence. So yes, so I will start like Jean-Loup by saying to you, Thibaud, what I thought generally about your work. So I had a very good opinion of it, and I really enjoyed reading your manuscript and all the very nice results it contains. I must confess that I'm not very fond of growth models, so but maybe after I read your document, I can change my mind. I feel it's a very nice work you have done in this direction. That can say you set some basis for studying this kind of growth model, and you show some results that makes them much more interesting than what they were previously, at least in my eyes. So I want to congratulate you on doing this work, especially like Jean-Loup said, with a lot of technicity. That it's not easy results to obtain, in particular the theoretic results you got. And also I enjoy that you push very far into the theory, you still also really care about the applicability of what you are presenting, and you do some analysis and you show the implications of what you have done for analyzing real-world networks. So that's a very nice and complete work in my opinion. So I wanted to start by saying this because my questions will be naturally more on the limitations of what you have done, but it does not mean that I did not appreciate your work. On the opposite, I really liked it. So let me just ask a few questions about that. First, about the motivations. So you developed the theory of growth model in your manuscript for generating networks, but I feel that you did not. It seems you did not try to compare to the growth of real networks. So did you consider this? Did you try to see if the growth model you have can reproduce some kind of growth that we know in a real world context?
Yeah, that's a really good question. And so for all the work on Twitter, I didn't do that for the good reason that we had a snapshot of 2012, and so we didn't have any dynamic. But for the co-publication hypergraph we have, actually we have every publication from 1990 to 2018, and so we could do that, and that's on the pipe. Indeed, and especially for the so there is especially for the mobilization of grants, the idea would be to look at the trajectory, for instance, that some nodes had in these real-world networks before they have grants and after they have grants, and also for other nodes which didn't receive grants, how they evolve without receiving a grant at a time t. But so it's actually what we started to do. And the idea, and so we started to do that. We had some complication for the communities, for instance, because when you look at communities, if you want to study a node in a community in 2018 and 2012, for instance, well, maybe they might have change of communities during those times. So how do you deal with that, and so on? So that is the first point. And another point we would also be interesting to go on, but it's maybe more difficult. It's like actually here in the model we have time step, and at every time step we add node and edges. But in practice, if you look at 1 year, well, maybe the number of nodes that are added each year might evolve during time, and so maybe one time step might not be 1 second, but it might be you might have to make it evolve with time. I'm not sure if it's clear, but
yes, I think I understand your answer, and I agree that's a good motivation to study this kind of model. If you can incorporate the variability over time of the way they evolve the network, it's even more interesting. So let me ask the second question about the limitation of growth model. So in your manuscript, you mostly care about the results, the network you obtain as the result of the growth, and you discuss about the properties of these networks and try to reproduce the properties of some real-world networks you observe. So the reason why I said I did not like much growth model before is because I feel they are poor to this purpose. One reason is that we know that, for example, if you care only about the degree distribution, we know that when you try to generate a network with a growth model like, for example, Barabasi-Albert, to say the simpler one, you will get the degree distribution, maybe the power law degree distribution you like, but we know also you introduce some more properties. So you don't really get one network chosen at random uniformly among all the networks having this degree distribution. You get for free, maybe you like, maybe not, some other properties. So I want, for example, which you don't get in the Molloy and Reed model. In the Molloy and Reed model, it's up to the small things about multiple ages and etc., you get more or less something chosen uniformly at random among this specific degree distribution. So what about the models you developed? For example, the model you did to reproduce any degree distribution. Do you have some hope to say that it choose one network at random uniformly among those having this degree distribution? Could you show this? Or do you know for sure that they have the same kind of limitation that we can know for the Barabasi-Albert model, for example?
Yeah, indeed, that's a nice limitation. And I think the model also have it. I don't see any reason why he would be different. So yeah, I think the limitations will be the same about this point. You don't pick randomly, uniformly among graphs, and if you have some hidden properties, you will find them here too. So yeah, for instance, maybe we can find about the fact that all nodes will have a higher degree. This is known in a lot of networks, like Barabasi networks and so on, because when you arrive first, then you will receive new links and you will have a high degrees. And here, I guess it will be the same. So maybe the attachment function will might have some impact in one direction or the other direction for those properties, but for sure they will still be here, and it will still be non-uniform. So yeah, I think the limitation is still here, and I don't see any smart way to circumvent this.
So let me propose one thing. For example, you talk about the odd nodes in the network. So what happens if you start with all the nodes already there and no edges, and you try to add only edges? You don't add nodes one by one. Can you remove this kind of drawback? Do you think it's feasible?
I think it would be easier, but then first it's not random growth anymore if they are all here. I think it would be easier, as you said, in the configuration model, for instance. I guess you really pick you really pick uniformly. But if so, I think it would be easier to do that if you do so. But you would also, of course, lose the advantage of random growth, which is the idea that in practice networks indeed have some growth, and so you might be tempted to look at the evolution, even if often, as you said, we don't do that. We just look at the infinity, and so we don't have this idea of growing. But we have that. You can also have some deletion of nodes that make it more complicated, but so. And so you would lose those advantages while but you will win, as you said, the uniform peak. Yeah, the same thing, I guess, it's a trade-off.
Okay. Maybe I will move to another kind of question, and I would like to talk about the model you did to reproduce a high level of ICC, your interest clustering coefficient. So you mentioned in your manuscript that when you make in your model the ICC goes up, when you augment the value of the ICC, you will naturally have the mean degree that will also augment the mean degree in the networks. So I wonder if it's a fundamental limitation, or if you can avoid this. Because what I would like to do, of course, in a perfect world, is that I would like to choose the mean degree, to choose the degree distribution, and to choose the ICC independently, and to have some network like this. So as far as I understand, it's not really possible in your model, but maybe I'm wrong. And if it's correct, can you think of a way to avoid this drawback? I don't want the number of edges to augment when I make the network more clustered following the ICC.
Yeah. Yeah, I think here again, yeah. So if we wanted to decorrelate the in degree, out degree, and interest clustering coefficient, we would like for sure to change the model. And I think the problem we have here is, okay, even if we have actually a bunch of parameters in the model, there is not enough parameter to separate them in a sense, which means that for the in degree and the out degree, we depend on those parameters. But when I made the simulations, and I was asking myself, okay, so I want this in degree, this out degree, this interest clustering coefficient. What are the parameters that I could choose? I had a set of equations to solve, which were not high enough, I think, if I remember well. And so to separate that, I agree it would be a really nice thing to do, because here it's really problematic to not be able to find all of them. And the problem, if I remember well, I think it was because when we do this K22 event, actually we add an edge to close the K22, and doing so, we change the in degree and or out degree in a way we don't really control, if I can say, because when you follow a K22, it's not easy to know in which node you will end up on which degree and so on. And so it changes the in degree and out degree in a, let's say, unexpected way, even if we can compute it. But so, yeah, if we wanted to change that, for sure, we would like to have a smarter K22 event. But here again, I'm not sure how to do this in a smart way like that.
Okay, but no, but I think your answer is clear, and it also unfortunately killed my hope. I wanted to ask if I fix the mean degree and I want to augment the ICC, can I do this by disturbing the degree distribution? But I feel your answer says no, actually. It's not related to the degree distribution. It's just that when you close the K22, you will naturally have more edges, and that's what is difficult to control, right?
Yes, sorry to keep you hope. Yeah, no, yeah. So,
than staying with a wrong hope.
Yeah. So yeah, for that, I think for that this model, yeah. So I don't know if we can have some, if we can prefer some models to other when it's your models, but for me, yeah, this model is less good than the other, and especially for these reasons. Yeah, because you don't really control anything, and it's not really clear how the ICC and integrity will interact. So
I see.
Yeah.
So maybe my next question will be about the hypergraph model, and maybe it's the last one, or maybe there will be one more, depending if the president allow me to ask one more. So about the hypergraph, I was wondering that because you took the definition of the degree, if I remember, the degree in the hypergraph is the number of hyper edges the node is involved in.
Exactly.
Right. So I was wondering if in your model at the end you control in some sort the number of co-authors you have in the co-publication graph, because it's not part of the degree. It's not, you don't count the number of other people involved in the hyper edge. You just count the number of hyper edges. So do you have a kind of control on this? And can you reproduce, I don't know, the mean number of co-authors accurately, or maybe even the distribution of number of co-authors? I don't know. Is it something that is controlled or not in this model?
Yeah, yeah, that's a good question. So this is not something that it controls a priori. It was, I think, a voluntary choice to do that, because here, since we choose, I mean, we choose nodes depending on their degrees, and so the idea of the degree was the number of papers they published, but not that much number of co-authors. For the preferential attachment function, I mean, we believe that people tend to publish more if they have already published, and not if they have published with a lot of people. This is something we looked in the real-world network, how many co-author people had and so on, but we didn't look in the model how to recover it. I would think about, so yeah, I think there is two things that might be done. So first of all, I think it wouldn't be that easy, because it will depend, of course, of the probability matrix, because in this model, if you remember, there is a matrix P. Yeah, sorry, the other model. Yeah, you have a matrix P, which is which represents the probability for two communities to publish each other. And so, for instance, if everything is a diagonal, it means that you will only publish with people in your communities, so to a small set of people. And if it's uniform, that you will publish with other people from other communities, so probably with more than people. So for sure, it will depend on this speed. And so for sure, it won't be that easy to compute too. And I had another thing. Yeah, and also I have seen some works that were interesting where they represented, because here in the, if I just come back to the presentation of the co-publication hypergraph we have made, we took each node as an author, and a hyperedge is a set of authors. And I have seen recently a paper that made the contrary, which means each node were a paper, and each hyperedge were a set of were an author which gather all those papers. And so maybe if you wanted to be interested in a model like that, you could just reverse the way you see this hypergraph, and this might be enough. Maybe I mean this might lead some clue like that.
Okay, I see.
But for now, we didn't look at it, and we don't have some clues. Just that depending on the matrix P, you will you will publish more with the guys on your community or not. That's all.
Okay. So I just want to ask Clémence if I should ask. If I should rather stop here.
No, you can ask a question if you want.
Yeah. Okay. So it's just so I will ask a very quick question, and again about theorem 2, like Jean-Loup did when he asked you for an intuition of the asymptotic condition. I have another very basic question, and I hope very easy to answer. That so your condition is asymptotic on what should respect the probability distribution, so that you can reproduce it by your growth model. So, but in practice, the distribution we observe, they are truncated. So there is no behavior at the very large n, or at least there is no behavior at infinity. So how do you deal with that when you compute your f? Is it a problem, or is it just something you stop the computation of f at some maximal value and that's all?
Yeah, that's a good question, and I think that's one of the main point of the application on real-world networks, indeed. And indeed, all the proof is for t goes to the infinity, and so it works well for theoretical bounds, but for practical bounds, indeed, you won't do that because you will probably stop at some point. And so I think that in that way, the proof doesn't really apply, or at least it applies for the mean, but you won't have any idea of the concentration and so on. And so indeed, that's why I think also this is reinforced, this is reassuring, because we find that it's not totally, I mean, we have the same behavior, but indeed this is just a practical proof, and you can't apply your concentration rules and so on when you know you will stop at some point. So yeah.
Okay, I understand that the theoretic framework does not capture this kind of truncated distribution, but I agree that practically it's very convincing when we see the result of what you can generate.
I was kind of sad that it wasn't. And so, yeah, I saw maybe, so either you can continue the distribution by saying, okay, we know that after some point it will look like that. But yeah, it's not really, so no, it's not captured.
Okay, but thank you very much, and I really enjoyed the answer you gave as much as your manuscript. So thank you again for your work and your presentation.
Oh, thank you.
Thank you, Christophe. So now we will listen to the questions of the members of the committee who were not reviewers. So we will start with Augustin Chaintreau.
Hello. First, I checked actually Toronto is a little further from New York from Nice. I wasn't sure because of the...
Yes, but you're not a reviewer, so this is why you speak after.
I was thinking Pawel. So you should.
Yes, I have no such rule for the committee members who are not reviewers. So.
Okay, got it. So you can tell it's a jury made of computer scientists who look for rules. Thank you so much, Thibaud, for the thesis and the presentation. I counted. I have 11 questions, so I'm going to summarize no more here because it's way too long, but it's a good sign. First of all, I want to say, a word of what I appreciate about, the approach. I completely agree with what Christophe has said about the limitation of gross model and how they can be basically too simple. I still want to, say I'm a big fan of them for the fact that they sometimes are critical to understand new emerging phenomenon that we don't basically comprehend with the entire conceptual tool we need, and those models essentially synthesize to the simplicity. And what comes to mind for me immediately is how we learned recently from work by Avin and others how preferential attachment may connect to including more discrimination in large networks. This is a very hot topic right now, and most of I think the work we're doing in my lab is coming from gross model that are in some way the birth of that, and I think work like yours is really, I think, exemplary in trying to unifying things, and so that's really refreshing. After reading so many papers on machine learning, in a very traditional way, it's very nice to see that. So I really like that a lot. I had some questions that were mostly a couple of perhaps local point about your gross model, and then I have a question about other stuff. So the first one that I'm actually kind of still wondering in my head is why this function f? You have two parts, with probability p you add a node, with probability 1 minus p you add an edge. And that makes sense. And of course, higher degree should appear more. How much more? That's what f counts for. Makes sense. Everything is intuitive. Now, why is f the same, when you add a node and when you are adding an edge? To me, it looks like a different thing. You add a node is now, added to the network. That's the first time you add it. Maybe there's another function, g or h, whatever you call it, that is at birth, and it's a different one. And the effect there, when you add a new node should not be the same. And does that matter? Maybe it's totally inconsequential, but I was just wondering if you thought about it.
Yeah, no, actually, I never thought about it. I never asked the question, but it's true that indeed you might think that this is different phenomena, like, when someone arrives in a network and connect to someone, it might be different than just when two people connect. So that might be interesting to study. That might be quite hard, both in real-world network and theoretical. In real-world, because at some point you don't have the idea, you just have the degree and you don't know how nodes had been created, if it was when someone arrived or not. And in theory, it would be more or less the same problem, but maybe that we can circumvent, because the degree of a node a priori is the sum of these two phenomena. But maybe you could just keep those 2 degrees separated, and just in order to keep track of the thing. I'm thinking about finding the attachment function f. So, but for sure, that would be an interesting work to do, and I never heard of it, and I don't know why, because now that you have said it, it looks natural to do so. So I don't know.
Well, I don't know if it's promising, because what you're doing, let's call the first function f birth as opposed to f recurrent. That one is just going to be there when you add a new node, which is a relatively infrequent. It's 1 over mu, whatever it is. So maybe it doesn't really matter. You could put whatever you want, and that actually everything that matters is the second function f. But I was just,
it happens a lot, because even as you say, if it's just one another, right? Let's take p equal 1/2, for instance. Then 1/2 over 2, you will have.
Oh, sure, yes.
And so you will have 1/3 of the half edges that will be from this function, and 2/3 that will be here. So
yeah, but p is typically 1 over the expected degree, right? So it should be not huge.
Yeah, depending of your expected degree, indeed. P will be not that huge. It depends on your network actually.
Well, yeah, you're right. You have networks with small average degree because there's there's a lot of disconnected nodes.
Yeah. I guess there is some with way smaller. For a social network, you follow hundreds of people, so it's quite high. But I guess I don't know a lot of biology, but maybe for food chains, you just eat 2 or 3 things. I don't know. I don't know a lot, but
okay. Okay, great. Thanks. That's very enlightening. One question, another one I had. So again, very small local question. There are many growth models where you essentially say it's either preferential attachment with some probability or random. And those networks, those growths are nice because you have a little bit more flexibility. Sometimes it's true, there are things happening at random. Can you account for that by essentially having that included in the function f? So essentially, that's not a different model. It's your model, or is that actually a different non-equivalent class of growth? I'm just wondering.
Yeah, actually, in all the models I have introduced, I kept this part, so it added other parameters, so it complicated the model, but I always kept this part to have preferential attachment plus random. The 2 reasons behind that was, first of all, well, why not? Because you just have to pick it to 0 if you don't want it. And also because with some model, especially for instance, the one with ICC, sometimes or also with hypergraph, sometimes you just add nodes alone without edges. And if you do so and you don't have this B, then it can't connect if it's by preferential attachment. Yeah. So it has to keep that. And for instance, here on this model, if you look at the Chaintreau distribution, what I recover here is indeed, so the Chaintreau would only be I, but actually here I lied a little bit because it's a generalized version of the Chaintreau distribution. Okay. When you have I plus what you're talking about. And here it's this B. If you take B equal to 0, then you come back to the classical Chaintreau.
Okay, so you basically can account for it in the function f. Cool. Then I had, well, I was going, I actually, people asked some of my questions, thanks them, because otherwise I would be, wasting more time, but still about this, I did this condition for G being bounded. I'm still a little bit like you, we'd like to remove that condition.
Yeah.
So one thought I had was, isn't it the case that, and maybe you already have a counterexample of that assumption, that as long as no node is connected to a positive fraction, which is of course a complete degenerate case, if you have that, okay, that is crazy. That's never gonna. This function is unbounded. But as long as you don't have that, I mean, there's no one that is connecting alone to a fraction of the network, then you're fine. It's actually going to be bounded. Is there anything like that? Am I dreaming?
No. I was so frustrated about this condition because indeed, I mean, the theorem I find the theorem really nice, and there is this huge condition in the middle, which is like, but is it true? Is it not true? I don't know when I have a redistribution if this will be true, and I really believe it would be true in a lot of cases. Actually, what made me thought that I'm not totally sure now if it's true or not is that I work on the Poisson distribution, and I try to prove this condition, and I didn't manage to prove it for the Poisson distribution, while also it would be quite easy. So maybe it's true, maybe not, but it's just that I didn't manage to prove it. So that kind of broke my hopes about it's easy, it should be really easy and so on.
You mean if the degree is Poisson?
Yeah, if P is the Poisson distribution, I was like, okay, let's show that, let's show this condition, and then I was able to compute the attachment function. And so I had it in the table. But since I didn't manage to show that the condition was true, so I don't say it's not true, I just say that it was not that easy to prove.
Oh,
so
I see.
I was like, that's not a good sign, and maybe it might be hard. But yeah, as I've told before,
well, I just picture things more like, if the distribution is light-tailed, you're not going to have too much trouble anyway, because this is essentially the function f, and f is not large. But the other range is a problem. If it's not just heavy-tailed in the classical sense, but super heavy-tailed, the sort of crazy, as you say, f is I to a larger power than 1 or something like that that makes everything. But I believe that if that's the case, then you will almost obviously have a pathology in the network. So you can be pretty sure that most of the time, except for ridiculous network, you're not there. That. Yeah. So I was just hoping that there's a way to do that.
Yeah, I hope there is, but I didn't manage to find it.
Okay.
Yeah, because indeed, if you look at this condition, it's really just, you can just put it as the attachment function has to not be convex. And so saying it that way, you see how the attachment function will.
Okay. And one that leads to my, the last question about the growth, which I'm sort of trying to see, what some of the merit of unifying theory like that is also to see how we can revisit what we learn. You have another chapter on revisiting preferential attachment. So one thing we learned that, preferential attachment, although we can absolutely criticize it, still have been pretty good at keeping properties. It has the degree distribution that is commonly seen. It has a small world diameter property. It has some amount of, clustering is a little bit more complicated depending on how you define it. But so I was wondering, right now there is this sort of, singularity point, and now you have a model that is much broader. So can you show, for instance, as a function of f, when do you have a small world? Something like that. Now you have a gross model that is way more general. So is there any hope to generalize some of those? Because at the end, what we want is, we'd like to know that some of the properties. So if I ask you, for instance, is your gross model satisfying all properties that are classical, small diameter, etc.? I think your answer is no, because this gross model is very general. You could have even a constant degree distribution, and then I expect you won't have a small world. So do you have any idea how you could use that model to show that those properties are much more general than we thought?
Yeah, I think it would be interesting, and it's an open problem, of course. And I think to do so, we would still use the attachment function, because this is, of course, really the key parameter.
Yeah.
And so we would like to study, okay, what are the attachment function, the interval of attachment function that might satisfy that. So that's what we have done with this theorem for heavy tail. And we didn't look at other properties, for instance, small words. But yeah, I think it would be possible for sure to study it, and it would be interesting to do so. Yeah, so it's an interesting open problem.
Yeah, and I'm sure there's others. In the as Christophe was saying, the preferential attachment had this order by age that is very important. You are not as short-sighted as the traditional preferential attachment, but still there should be some order, and that creates some structure that I've seen to have. So I'd be very interested to see if some of the results that I found very anecdotal when it's about a single model are actually, they work for a bunch of function f, and then it's okay, that sounds more believable. I had a short clarification on your red theorem here. When you say f bounded from above, p is not EV-tailed, do you actually mean bounded by an exponential? Because heavy-tailed and light-tailed, do you mean light-tailed, or do you just mean, I don't know if it's light-tailed, but it's not heavy-tailed, just to get a, because they are different definition, and I was not sure which one you use.
For P or for F, sorry, or for both? You mean for P?
Yes. No, I understand F is bounded from above, that's unambiguous, but the consequence of it.
So for P, okay, so just let me find, maybe it will be easier if I can use the definition. So I took a definition of a heavy tail function, which is just that the probability of x being bigger than I has to be yeah, I think it's here. Condition. So here is the definition I used. I said that a distribution P is heavy tail if it decays faster than an exponential. And so I just show that this function goes to the infinity if f goes to the infinity, and this function was bounded if f was bounded.
Okay. Okay. So it's really yeah. So you could say light-tailed actually. Not because not eVTOL is a bit ambiguous. Some people may.
Yeah. So maybe they should, yeah. It was in the plans.
Okay. I don't think that's just a big difference actually. So it's no big deal. Okay. Great. I was going to ask one question. You mentioned your work about specificities of Twitter, type of degree. And actually, my main question was to understand in your chapter 6 on revisiting preferential attachment. So I sort of read it, but I'm trying to understand what is the intuitive message, the lay person understanding of this situation with what's specific with Twitter. That's a part I wasn't sure, because I understand how the degree, which is the by degree and the out degree, but what would we imply in practice to?
Yeah. So just by hand, maybe qualitatively the main.
Sure.
When you look at Twitter, the first thing you see is that there is a lot of bidirectional links, so link in one direction and then in another, and that won't happen in random. If you do random, it will almost never happen to have those links. And the other thing is that if you look at the correlation between the degrees, sometimes you have high degree correlations and sometimes not. And this is also unexpected if you do some random stuff. And so the model that has been proposed is to have those high bidirectional link and to have those difference increase the degree correlations. But to analyze it, so first of all, it was a directed model, so you have in degree and out degree. So you already have here a jointed thing if you want the degree, the number of nodes with high degree and out degree at the same time. But moreover, we had to add the bidirectional degree from our model because to have this correlation between these degrees, sometimes we had to remove this bidirectional degree and only consider the degree without bidirectional. And sometimes we had to consider the in degree, total in degree. And so we had kind of 3 types of degrees: the in degree without bidirectional, the out degree without bidirectional, and the bidirectional degrees. And so we had 3-dimensional models, which is of course quite harder to analyze. And so that was the main part of the framework to analyze these 3 dimensions.
I didn't get it with that level of precision, but I got that roughly from reading it. But I was trying to understand. Okay, now if the CTO of Twitter come in my office and tells me we have this model, how can I say no, your model is wrong? What's going to be the big difference that is going to be how does it translate? I understand your model is more accurate, but what was the main inaccuracies that you have to remove, in terms of consequence on, would you be wrong in, I don't know, assuming the link is reciprocal in some situation? Or,
in our model, you mean? Or in other model? In our model, what would be the problems with our model and what would be the point?
Well, I think it's fair to say that your model is more accurate than whatever would be the vanilla preferential attachment. But traditional used model are nice because people know them. It's very reassuring, very familiar. So I was wondering, what is the motivation to, beyond just being purely accurate in your sense, what is an implication, a consequence that is really means that we have to use your model?
Yeah. Well, I think the bidirectional thing is really a strong point because we have seen that Twitter is both there is a lot of them, and Twitter is both interest and social network, and social probably have a lot of bidirectional links.
Right.
And forgetting about these bidirectional links, I think is really in Twitter having a strong number of bidirectional links is a really important property, I think. And I think.
Okay, I see. Yeah. So you think it's important to be there? Okay.
Even for the property, that's enough to justify it.
Makes sense. I don't know how much time I have left. Maybe it's already negative. Tell me, Clémence.
There's no fixed time. If you have one or two questions, you can.
Sure.
You can
Okay.
ask them.
I was going to check. Maybe to end, on some more general one. I had to. Sorry, if I can ask two, I'll ask two. One of them is related to. I'm trying to understand your interest clustering coefficient in comparison to the previous one. So the previous one, it's a triangle. It's not any triangle. It's actually a triangle that is directed by two edges, one after another. So that's the only thing you look at. You don't look at, for instance, if the node on the left follows two people. Is there going to be an edge between them? That's not. Doesn't look like it's relevant to TCC or CCC. So you take that situation, and now you compare it to another situation where you have actually two triangles. Two open triangles that overlap in a way that essentially creates this. So then you compare the absolute value of what that, and 3% is not 0.5%. I get it, but I don't see why they should be the same percent. I mean, one is a single triangle, the other one is two triangles with an overlap. It's I like it. I just don't see why you compare it to. Except for the name, I don't really see what they have in common. So if I want to actually care for this result, I need to understand why should I expect them to be relevant to
sure. So first of all, just to clarify, maybe here we don't have triangles, of course, right? Because here we don't have points, so it's really more a rectangle, just to precise that. And then
sure. But open. But what I mean is that the open K22, which is basically what you have on the right.
Yeah.
You're asking whenever I have. If you draw the triangle, I'm not going to draw it on my screen because you can see. But if you look at, you take everyone in the bottom and you take the node that they point to. You have an open triad, and then you have another open triad that overlap through one edge. That's what I mean by triangle. And you're kind of saying when you have two open triads that intersect, it's likely that this close the loop basically, and yes, I think that's true. That's what I meant.
Yeah, I get the answer to the question. Okay. Indeed, it's more or less in the name. It's more or less because they have the same name, but the idea behind that is more that. Sorry, the definition we introduced were always a definition which is the probability to close an open structure. And so in that sense, we can compare them because it's always, the classical clustering coefficient is the probability to close a path of length 2. Here it's more or less the same. You want to close the path of length 2, and so this is a probability. And here it's a probability to close the path of length 3 with some direction. But so this is in that sense that we believe we can compare them because it's the probability to close a path of length 2 or 3.
Well, at least as a remark, I would say, the probability that you close something that is made of more complicated things with more nodes, it's just going to be higher. I mean, it just means there's more density around stuff. So you should expect it to be higher, I guess.
Yeah, that's an interesting point. And we started to work on that, and then we never ended it. But we have observed that in random growth models, such like Albert ones and so on, surprisingly, the probability to close a path of length L won't depend on L. And that's a really surprising result. But if you have a path of length 2 or a path of length 5, it didn't change anything because it's known that in this random growth model, the authoritativity is equal to 0. So when you do a random walk and you go to 1 step further and 2 steps further, you already forgot your degree. And then doing more steps, more or less, doesn't change anything. So that's the idea. Of course, the proof will be way more complicated.
Okay.
But the idea is that, but indeed, it's not that intuitive. I agree with you, and we were quite surprised when we thought about it. But yeah, so that's.
And another dimension. If you compare to the TCC from before. And I guess I'll skip my last question in the interest of time. So please, that's the end. usually the difference between TCC and CCC is a little bit of the type, is it our connection sign of statuses? You know, does it mean when you follow someone, you're essentially showing that they are of more importance than you? And that's one theory by some researchers, that, you know, there are networks like that. Maybe Twitter, you know, following someone is a sign of deference and some. So in that case, you will expect lots of TCC, because knowing that I follow someone, this person follows, that means it's essentially an even higher status that I should follow, sort of. And the other one is the opposite. It's like, no, it's a relatively flat, spontaneous structure that doesn't try to, you know, achieve an hierarchy, and then actually you would have more of those. But in your situation, you're really more connected to a status thing, because all edge flow in the same direction. So, so maybe that's one thing that, you know, could be of interest. You know, if you never see the triangle closing the other direction, it's kind of interesting, because the difference between TCC and CCC, how much more you have of TCC rather than CCC, is usually a sign that the network is hierarchical. It's not a flat thing. It's like there are big people and small people, whereas in the other case, no. So you should perhaps be able to use that also in your metric to determine if that's the case. And I already used many people, so I've never been in a jury with 8 members, so I'm going to stop there. Thank you so much.
Thank you, Augustin. So you will continue with the members of the jury. So Giovanni, Neglia, I hope I'm not butchering your name.
No, it's fine, thanks. Okay, thanks Thibaud for the presentation. I join the other people about the pedagogical quality of the presentation was nice. Okay, so some of the questions I had in mind were already asked, so perhaps I have only one perhaps for you. So there is this. So I remember when Arnaud was presenting one of the first time his his work on Twitter, and then he was telling us that actually a huge number of these account were actually haven't been doing anything. So kind of like one day they created the account, they started following a bunch of people, and then they didn't interact. So, and this led me a bit to think that perhaps when you, in all this social network application, the topology of the graph perhaps doesn't tell us much, no? Because now I wonder, have you thought about how you could you could integrate in your work some information about what's happening on the link? I mean, if people are more or less active, if people follow, interact more with one person than with another. So I don't know. I mean, it's I understand that you have done different, you have different contributions, so the answer is probably not going to be the same on all of them. But what do you think? How could we? If you are Twitter, we have this information. We have the information about the activity of the person, perhaps also, like retweeting, liking, and so on. How can this be taken into account in a model? How can you perhaps, model this and capture in your growth model some of this information?
Yeah, I think having this information would be really, really informative, of course, but indeed, it's a little bit of a contradiction that we have only a snapshot of Twitter and we want to do a random growth model from just a picture. So indeed, it's hard to find good ways to study the dynamic of Twitter by having only a snapshot, but by having them, for sure, we would have been able to do so. And for instance, by choosing the way nodes attach differently. For instance, as you say, if people tend to attach a lot at the beginning and then not anymore, well, maybe just add a fitness or a function depending on the time that when people age, like become older, they will tend to attach less and so on. So for Twitter, we hadn't this option, but for the co-publication hypergraph, since we have it now, that's what we are trying to do. We have the number of publications for a bunch of 30 years. And so we are trying to look in the real world networks how publication evolve and how communities publish with each other and so on. And so we hope that, yeah, maybe we can integrate that in models. But yeah, for Twitter with just a picture, it was.
But perhaps my example was a bit misleading originally. So what I meant is that there is something that is happening on top of this graph, no? So, I mean, there may be people that are followed by a lot of people, but actually they never tweet, no? And then, I mean, you may think that they are irrelevant. Yes, people follow them, but and there are people that interact, and there are sometimes bidirectional link, but where one of the guys constantly retweeting what one of them is doing, but the other one no. So it looks like not all the link count equally. No, there is some information that moves on this link or some kind of interaction, and I'm wondering how could you try to? I mean, how could you try to build a graph that assuming that this information is available? How could you try to take this into account if you thought about how you could think about defining a clustering coefficient that takes into account the fact that perhaps, I don't know, some links are not real link, it's because nothing happens, but other links are really a weight. I don't know if you have thought about this.
Yeah, so we didn't thought about this since we didn't have the data to look at it, but I guess the main thing to do would be to maybe look at the different graphs, because indeed in the graph we are building with our model, it's a graph of followers we are presenting. And so indeed there is just the information of there is an account which follows another account. And for instance, as you said, maybe we could say that, okay, if someone tweets a lot or retweet a lot another account, it's really interesting. But in that case, the graph should be modified, for instance, putting weights on edges and saying, okay, the weight would be the number of times an account retweeted another account, and so on. And then you can have some models for that. So I guess, yeah, if we had those data, the best thing to do would be to first to find a graph that would represent indeed those data, and then find models for them. Yeah, I don't know if it answered correctly or not.
I mean, I don't think there is a correct answer to this kind of question. And for the graph in which you said you have more dynamic information, so these co-authorship graph, no? It's do you think there will be a way to capture? Because perhaps there are some information about the strength of a link among two people may also be captured by perhaps the number of links, no? Perhaps in that case, it's intrinsically captured by the graph structure, but
yeah, exactly, because in that case, if two people published a lot together, we can say that indeed they are. Sorry, I don't know what it is, but if two people publish a lot together, you can say that they are really close together. While if you just publish one time with someone, maybe it's just that you meet him and so on. So indeed, actually there is two ways to see this graph. So I think with hypergraph you keep the information, but if you, for instance, do a projection of each hyperedge, so a hyperedge is a set of nodes, and you can project this hypergraph into a graph where each hyperedge is transformed into a click between all edges. And if you do so and keep the weights, then you will have high weights between two nodes that have published a lot, for instance. And you can also chunk the weights depending for instance, if you have a lot of authors, we saw about it because sometimes you have a paper with 5 authors or 10 authors, and then you will do a lot of edges, but maybe it's not, I mean, it should be equivalent to a paper of 2 authors, and maybe even more. And so maybe you just have to adapt the weight, but you can still keep track of that this way.
But okay, and I mean, for example, for the clustering coefficient, do you have an idea about how you could how you could add, I mean, I don't know if I don't know also much this field, but I mean, for clustering, are there probably there are no weighted clustering coefficient, something for a weighted graph?
Yeah, for weighted graph, there is clustering coefficient, so this might be a study. I'm not aware to a clustering coefficient for hypergraphs, but for weighted graphs there is, so you can take the hypergraph, project it in a weighted graph, and study the clustering coefficient. We didn't do that, but we might do that, but we didn't look at it yet.
Okay. Okay. Thanks. For my side, it's all.
Thank you.
Okay, thank you, Giovanni. So we will now listen to the questions of Pawel. Pawel, are you here?
Yes.
Okay, hi, hello, it's Pawel, right? For me?
Yeah.
Okay.
Maybe I'm mispronouncing your name.
No, yeah. I was thinking about something else, or maybe it's my fault, sorry. Yeah, thank you so much. First of all, congratulations. It was, very good results, and I like your presentation a lot as well. I enjoyed it a lot. So I don't know how much time I have, but I can simply ask a few questions, maybe comments first that will turn into questions. So first comment, it's not really any concern or anything, of course, because I'm actually personally very bad with literature search as well. But I spotted, for example, that you mentioned some stochastic block model as a graph with community structure, but there are some other models, well-known and widely used models like LFR and ABCD. So just for your information, if you don't know them, I can send you some links offline. And also, that's something that might turn into a question. I think we now know that very often networks kind of have the so-called densification, so the average degree grows with time. So I didn't think about when I was scanning through your thesis, but maybe some of the results can be adjusted to the situation where a new node that joins the network, instead of creating M hyper edges or M edges, maybe this can be a function of T. Is that possible, or is it interesting to you?
I think it's possible. I think it's easy to put this function of T in the model, and I think it's really hard to then do some computation on it theoretically. And I also think that maybe another way to do so, I mean, if the goal is to say, okay, in real-world network, things are happening faster and faster, but it's always the same thing, like you follow someone and so on, but just you do it faster and faster. Maybe you can also just keep the same model and then make the time go faster. I mean, just say that at the beginning, for instance, 10 time step is the equivalent of 1 second, or I don't know. And after that, 10 time step is the equivalent of 1 millisecond, and so on and so on. So I think, I think adding this function of T is possible, but maybe complicated for computation. And I think
but of course, it's not only a matter of time, but it's a matter, of the initial, say, degree of a node, right? So I think this is doing. So I think what you're saying is maybe you can kind of merge, because that's what typically people do in a Barabasi-Albert kind of growing model. They look at the say 1-out model, and then they simply compress M verses into 1. So here you would have to keep compressing more and more of them into one node. So I don't know. This is just I'm assuming, since I'm not the reviewer and really read extremely carefully your thesis, although I enjoyed it and had a quick look. I guess I'm more like maybe providing some suggestions for your future research. So I think growing is definitely of interest. So if you haven't thought about it, and maybe your models can be adjusted to a growing situation, then that's definitely one possibility.
Yeah, I agree. And I agree. It's a limitation of a lot of random growth model, since we suppose it's constant, and as you said, for most of them, I guess it's not. So it would be interesting to add that in models for sure. Yeah.
And then another general comment is that you use, say, classical tools like Hevding-Azuma inequality for showing concentration, but in fact, in your model is something stronger. I don't know, maybe first of all, correct me if my intuition is completely off, but it seems like your random variables are in fact self-correcting. So what do I mean by that is that if you have, for example, too many, for some reasons, too many vertices of, say, in degree k, or you may also look at the clustering coefficient, whatnot. So if something is off, maybe you start artificially from some network which has some weird degree distribution. Then if I have too many vertices of degree k, then with higher probability, I'm going to connect to them. So they will be decreasing. On the other hand, if I have fewer than your expectation, then of course, it will be less likely to connect to them. So these random variables seems to be self-correcting. So you can start from, say, a graph with 0.2 n nodes, maybe some weird degree distribution, and then you play from there your growing model. I suspect that things will be self-repairing, and after a bunch of steps, you will actually converge to the limiting distribution that you predicted in your model. So of course, you will need to have different tools, and my suggestion here would be to use, I don't know if you have experience with that tool, you can use the differential equation method of Nick Wormold that shows that you can control the behavior of a random variable during the stochastic processes. So I think there are many questions in that one comment. First of all, do you think my intuition is correct? And indeed, there's this self-correcting behavior. If yes, is it interesting? Because maybe it's not interesting. And if it's both true, then my suggestion is that you should look at the differential equation method if you don't know it, and it should be a tool to prove it.
Yeah. No, yeah. So yeah, to be honest, I don't know if it's true or not. That's a good question. If the intuition is good or not, I don't know. I get the idea indeed that if you have a lot of nodes of degree k, then they will leave state k, and then there will be less nodes of degree k plus 1. I still think, of course, there is something that might happen that might do that the concentration is not good enough. And concerning the differential equation, so I don't know a lot about it, but I mean, I heard a lot about it, but I didn't look that much about the fact to go, because I think the differential equation, sorry, I'm just yeah, I think the differential equation is a continuous equation, and so you have to go from discrete to continuous time, which might be interesting, but might have some difficulty to prove. And I think the last chapter is one way to get around that, because the idea was to represent the degree distribution as a function of a Markov chain, and to show rigorously that if you look at the steady state of this Markov chain, then it's the same of the degree distribution, more or less. And that way, if you see it in a way of Markov chain, that then, for instance, each state, sorry, will be the degree of a node, and you will leave them with the probability transition, so it will be more or less this thing. And so, yeah, sorry, I did not remember where you were going.
No, but yeah, it's a good discussion. So yes, I think They're just two comments. So I think, yeah, you're not convinced, but I think I'm kind of 99% convinced it is a self-correcting behavior. So, the reason for that, I think, is that, you know, the new node that joins the network is always of in degree 0, say, right? So I think that will kind of stabilize the first players, and then everything else kind of by induction will naturally be happening. But anyway, so of course it's more technical than that. But I can send you a few papers with similar problems and similar solutions. And then the differential equation method I mentioned is exactly the tool for discrete processes, right? So you don't have to invent the wheel. That's a good thing. So that's a good tool to learn. So I think it seems like it will be important in your future. Because yeah, this is a good tool which essentially tells us that if the Lipschitz condition is satisfied, so you still have to bound the expected change, the maximum change that can happen, as with Hedwig and Zuma. But then you have additionally the drift. So you have the expectation, and then the conclusion is that the random variables are following the solutions to the differential equation, which is of course continuous problem, but it applies to the discrete world. So yeah, I'll send you a link. So again, I see my role, maybe I misinterpreted my role, but I see my role as more like a guidance maybe for the future, because of course it's just the beginning. Your PhD is just the beginning of your bright future, it seems, because you've done a lot of good jobs already. So I think this is a good tool to learn. So if you're not familiar with that tool, you should definitely have a look. I'll send you some links. And then maybe last general comment before being more specific. Yeah, this the models are in my mind two reasons, right? One is to be as a null model. And indeed, then we would like to have you know, the random graph to be uniformly distributed from all the graphs. So I think that's what Christophe I think was complaining about a little bit. So I think that's one application, but the other application is actually to get understanding of the behavior of networks, and that's what I guess Barabasi-Albert model does, right? It tells us that we have power law because of rich get richer principle. So my suggestion here would be, since you have this translation between what is the degree distribution you want to get and you know what is the function f you want to use. So I would really be interested in to investigate a little bit more that and try to understand why we have this degree distribution in real networks. And your model can explain that because it seems like it's not only rich get richer principle, but something else is happening, which is embedded in your function f. So I think, you know, you start from the degree distribution, you do function f, and then look at the function f under a microscope. And what is so special about that function f that will give us some more intuition and possibly very important one in this field. So is it rich get richer? Perhaps, for sure, but maybe old get poorer, or you know, being too rich is tough. There's something else going on, and your function f can answer that. So no, do you have any thoughts on this maybe already?
Yeah, exactly. So I guess the main problem with that is that, of course, all the proof I have made is only for the model I have, but I as you say, I hope it might like another thing. And if I understood well what you were saying, for instance, we try to do what I understood you were saying on the co-publication graph, because we took the degree distribution of the co-publication hypergraph and we computed the attachment function. And so this is the attachment function from the real co-publication hypergraph. And after that, we can ask ourselves, okay, what does it look like? Okay, here it looks linear, so indeed it might be like rich get richer. And here, okay, it's also increasing, so rich get richer, but it's concave, and so it might have some some understanding with and so on. And so for now, we are doing that without any real proof that it's working, because the proofs are just for the rigorous proofs are just for the model. But well, maybe I shouldn't, but I really hope that this formula is general enough to be applied on other things. And so, yeah, I think it would be really interesting to study things like that. And for instance, to say, okay, yeah, here it's definitively linear. So Parabasi, Albert are true. The more you have, the more you get in a linear way. But, well, not when you are at the beginning, and so on and so on. So, yeah, I hope it will be one of the main applications of this work. But we'll see. Of course.
Yeah, thank you. So I think, I don't know, again, I don't want to use my time too much. I think I like asking questions, it seems. But yeah, I've put 4 questions for clustering coefficient. Maybe I'll ask one. So which one would be the best? Or maybe this one. So the spatial proportional attachment model actually was investigated. The clustering coefficient is known for this. And there are also known things about the directed diameter. So I'll send you links about that too. I think in your table you had question marks, but I think this is known. But its clustering coefficient is known in a very strong sense. So what do I mean by that is that it is known in the real networks as well that the clustering coefficient for a node correlates with its degree. So if you look at all the verses of degree k, then the clustering coefficient essentially scales as 1/k. So it's proved for a spatial proportional attachment model that this is indeed the case. But I was wondering during your presentation, is there an equivalent conjecture for your clustering coefficient, especially especially for this K22? I don't know. I cannot wrap my head around what would be an equivalent coefficient, but maybe there should be some kind of correlation as well. The larger in degree you have, maybe, or out degree you have, you should expect some different behavior of your clustering, local clustering coefficient.
Yeah, you mean in models or in the real world network, or in both? In models?
Yeah, I think in both. In fact, yeah. So in your model, I think you probably have more intuition at what's happening in your model, right? So yeah. Would it make sense to kind of dissect the clustering coefficient into nodes of a certain degree, and maybe some pattern occurs? So again, what we know for the regular clustering coefficient is that if you look at the clustering coefficient of nodes of degree k, it is actually scales as a 1/k. So so there's behavior like this, and it's proved to be the case for many models, but for real networks this is observed as well.
Yeah. So first of all, about the clustering coefficient we have studied here, it's what we call the global clustering coefficient. So it's the total number of triangles to compare to the local clustering coefficient, which is for each node indeed, and into which you might study if it's decreasing, increasing, or constant, and so on. But if we can still suppose that we can study the local clustering coefficient, and in the model, if we do so, yeah, I'm not sure. Yeah, I don't know what that would give. I guess the proofs that are used in a classical model might be used in this model and in this model. For this one, it might be more complicated because we have these things that explicitly change the clustering coefficient. But yeah, I guess it might be looked the same way, but I don't have intuition of what it would give. But
yeah, but I think so that would be interesting maybe to analyze, because I think again, practitioners know exactly what's happening in the real networks, and yeah, the average local clustering coefficient is a bit kind of misleading, because the main contribution will be from the nodes of very low degree, because they're it's a power law, right? So you have most of the nodes have low degree, but then those that are rare, they have high degree, their clustering coefficient is a bit different. So I think that's why it makes sense to just ignore those majority of the nodes and dissect those high degree nodes because they have different behavior. So if you haven't done that, my suggestion would be to maybe have a quick look.
Yeah, that would be interesting and to see how it's done. And I think it will also be interesting because if I remember correctly, I told you there is some common properties like we want communities and some specific ones. And I think the correlation, how the clustering coefficient evolves depending on the degree of nodes is different in some neural networks. So for instance, I don't remember, but I think for protein it's decreasing while for other it's increasing or something like that. So it may also give some insight for like, okay, this model is more suitable for protein but not web or on the contrary. So for that reason, it's also an interesting property to study.
Okay, so maybe let me skip to hypergraphs for a moment. I have only 3 questions there, but I'll maybe ask 1 or 2. So my first question is the following. So I really like that, of course. I'm a big fan of higher order structures, and that's just the beginning again, because I think the social networks are, of course, much more complicated than hypergraphs. But I was wondering when I was looking at your thesis, I can do the following coupling. So you play your model on hypergraphs, but maybe what I see is that every time a hyperedge is introduced, maybe new node joins and I put a bunch of hyperedges. I can think about coupling to directed regular graphs by sending a directed link from this new node to all the nodes that are in at least one of the hyperedges I introduced. So these 2 processes are coupled. You look at the hypergraph, I look at the directed graph. And the degree in the hypergraph is probably in degree in my model that I observe. So
plus our degree, because I mean, when you add a hyperedge, then you increase the degree of every node you pick. So both the node you have picked, but also the old one you will connect one. So
yeah, so my coupling would be that, if let's say you create a hyperedge of size 4, then I see 3 edges, 3 directed edges from the vertex you just introduced to the 3 other members of the hyperedge.
Okay.
Because I think this is more or less, unless I misunderstood the model, but I think this is more or less what you do in the model. You kind of select members of your hyperedge independently with probability that is maybe a function of their degrees. So I can perhaps generate one directed edge at a time instead of building a hyperedge. So maybe it's a bit more complicated, right? But I think such coupling can be done.
Yeah, I don't know if it would be equivalent. Because here, when you add a hyperedge, you mean instead of adding a hyperedge, you might add only one directed edge, and you say it would be equivalent to add all those directed edge at different time steps.
So I think instead of adding hyperedge, I will be adding instead of adding hyperedge of size S, I would be adding S-1 directed links.
But
then hopefully the in degree is going to be the number of hyperedges. And again, maybe it won't work, but just a fruit of thought. By that coupling, maybe you can, because that's in some sense the 2-section projection in a graph, right? So maybe not really, but something of the same nature. So maybe you can simply instead of trying to understand the degree distribution in a hypergraph, maybe you can translate this to the in degree of directed underlying projection, and then use if the model is still fits into the other well-known models, maybe you can recover your observations.
Yeah, but to do so, we have to be sure that it's equivalent. And yeah, first of all, when you add your node and then your directed edges, the node you're adding should also have its degree increased. But maybe you say you can just put a loop or something like that. And then when you are to a hyper-edge step, which means you don't add node, but only a hyper-edge between a set of nodes, to have something equivalent that would increase each degree by 1, maybe you could put a cycle, maybe not one node going to each other because, or with a self-loop or a cycle. Yeah, actually, so yeah, I think we might be able to analyze it that way. And actually, we did something which is not exactly the same, but a little bit similar, because one of the work we were trying to do was to show that this hyper-edge model and the degree distribution of the hyper-edge model is equivalent to a model, to a bin model, where at each time step you like only add, increase the degree on one half edge, and you choose this correctly such that it would be equivalent. And so we believe this is probably the same thing, because actually when you add a hyper-edge, you just increase the degree of all those edges. But if you forget about communities, the only thing that matters is the degree of the node and not to which they are connected. Actually, when we build the network, you only look at the degrees of the node independently on who are the neighbors. And so you only have to keep track of the degrees. And so I guess you can do some equivalence between the hyper-edge models, the directed model you present, and maybe these bin models, as long as the degrees increase the same way at each time step.
Yeah, so of course, yeah, it's good that we don't know exactly how to do it in 5 minutes, right? So it means that maybe it's interesting to think about it more. Yeah, so that's good. That's great. So I also liked a lot, of course, the results on the modularity you have for hypergraphs and your lower bound. But unless I missed something, you don't have upper bounds, but of course, in your other model with communities, of course, it's expected that the partition implied by the ground truth should have the highest modularity. So all the other partitions, which of course there are many of them, should have smaller modularity. So it feels like your lower bound is probably sharp, right? So did you think about, or maybe I missed, did you prove that it's sharp, or do you have any upper bounds for the modularity?
No, you're right. You're right about the reasoning we have made, and we didn't prove any upper bound. But as you said, it's probably quite sharp because at least, I mean, we took a partition that made sense because it's the one from the matrix, but we didn't try to prove that it was that it was sharp and that the upper bound was not that far from that. I don't know how to do that, but I guess probably to look at some papers that have given some upper bound, like the one on Ernest Reilly made by Magnien recently. It may be interesting to have some ideas about that. But so no, yeah, here we just give the lower bound, and probably it's quite sharp, but we don't have any proof, or even we didn't check that. Yeah.
Yeah, so I think it won't give you sharp result, but certainly you can just simply take a union bound over all partitions, and that would give you the modularity bounded away from 1 for sure, but it won't match your lower bound. So I think definitely it will be super interesting if you can show that. that is sharp, but I think some non-trivial upper bound will be of interest too. So yeah, I would encourage you to try, but maybe it's not so easy. So maybe last question, or just maybe a comment, because yeah, you focus on modularity for this community, hypergraphic community. Have you tried to show some bounds for the hypergraph without communities for the first model that you have?
I mean, an old model. We didn't try to find the modularity for a bound for it. We just computed, but I think you've seen it. We just computed it experimentally to show it was quite low. Okay, let me just find the figure.
So experimentally, you mean you ran some Louvain or Leiden algorithm?
Exactly. We run some Leiden algorithm, and this is the green line here. So we run some Louvain algorithm, and I have shown that in the Avignon model, so without communities, it was quite low in comparison to what we had here. So yeah, but we showed it experimentally and didn't do some theoretical bound for this one. Yeah.
Yeah. So of course it will be small because you don't have communities, right? But yeah. But definitely you can prove some bounds. If you have an average degree m, the bound should be more or less like 1 over root of m. Because the idea is that, you know, when the new node joins the crowd, if you split in a nice way 50-50, you know, just two communities, then by pure randomness, one of the communities will always get root of m more edges than the other competitor. So we can use this. You can analyze this process by, you know, assigning a node to the community which the node has more neighbors in. And I've done this once, and I think you have actually Małgorzata Sułkowska, I think, around the corner. I'm assuming she's doing her postdoc at your institution. Yeah. I think she's also in the audience. Yeah, so I think she also worked on similar problems. So I think should be. Yeah, so it should be possible, what I'm saying, to apply similar tools that we used for the model without communities. But yes, you're right. Your experiments are unraveling the truth. It will be small, of course. It will be like 1 over root of m, yeah. Where m is the average degree.
Yeah, just like in those models. And I just wanted also to come back. So I agree with you on that, of course, that we'll probably find something like that. And I just wanted to come back also on the previous question and about the lower bound, just to precise that indeed it won't be sharp, because actually the bound we have found is really nice when degrees, when the size of hyperedges are more or less the same. But it's not that good when the size is really changing. So we have we have a parameter d, which is like the maximum size of the hyperedge, and so this bound is really good when you have hyperedges of the same size, but not that good when it's not of the same size. So these parameters might be also have an impact on the bound we might find. Just the precision.
Okay, but I think we both agree that you know, the partition from the ground truth should be you know, what at least asymptotically what the modularity is, right?
Yes.
All right, I think I should probably stop here. It was very interesting, so yeah, very good job, congratulations. And I think, you know, there's a lot of work for you, me, and many other people. So I think that's very good PhD thesis that opens a lot of interesting questions, and already it's a great achievement. So thank you so much.
Thank you.
Okay, so now we will hear the questions of or the comments from the PhD advisors. So we will start with Frédéric.
Yes, thank you. So I will be short. I don't have any question for Thibaud because, of course, I had a lot of discussion with him. So I just want to say that it was a pleasure to work with him, with Thibaud. Okay, first, because his PhD was some opportunity to work on a topic a bit different from what we do in Coati usually. So that was really interesting to have all this work and discussion on this somehow new field topic. Okay, it's graph, but a bit different from what we usually do. And it was also very interesting because Thibaud is a very curious guy. And thanks to that, we had a lot of really nice discussion about implication of the work, about what to define, and etc. So he was really active in this kind of discussion to make sense of the data we had and the model. So it was really interesting. Of course, he had a lot of nice contributions. So I just want to thank him for this years spent with him. So that would be all.
Thank you, Frédéric. Stéphane, I don't know if you want to ask some questions or make some comments.
Yes, do you hear me or not?
Yes, we hear
okay.
you.
No, I had some question, but maybe it's too long. First, I have to say the same thing. It was very motivating to work with Thibaud, and it was very nice too. So thanks to him. Thanks to him for the very nice presentation. Well, I had some questions, so let's say maybe I had many, but I will just ask one or two. There is a growing, people in the US are very worried about polarization, and I think Augustin told us about it a little bit. You had a book, very famous book by a girl, a woman named Susanna something, a book like 8 years ago. The name was exactly the name that mentioned Thibaud. I think the guy name was Eli Professeur. And so I was interested in the feedback between search engine and the recommendation and the network growing process. And so I think it could be interesting to introduce not a preferential attachment function F that would be indeed driven by a recommendation or search engine. So I don't know if it is, it may be very complicated because the degree or a simple function of the degree is something simpler than the result of a search engine. As example, if the search engine is returning you the fixed point of the iteration that Google used. So, okay, so I was asking to Thibaud if he thinks that this could be interesting to look at that and how we could. Okay, that was. Does he think that it is possible to study if the search engine are indeed increasing the polarization, which is what people claim and are worried about indeed. Especially in the US, it was completely crazy the last 2 or 3 years. Well, you could try to introduce, I don't know, you could try to introduce this f of d to be something partially driven by recommendation algorithm, which would not be the degree or would be something, okay.
So yeah, to answer the question, I think of course it's interesting to study. It's an interesting question to study, of course. How my work might help in looking at the polarization in search engine, I'm not sure to see directly. Yeah, I'm not sure how it will be really relevant to the question, but of course it's something really interesting to do. And yeah. But maybe I just didn't really understand the question correctly. I don't know. Maybe if you can. I don't know if I answered the question or.
Well, but that's I don't know. I think it should be okay. Otherwise, the simpler one is is not simpler, but okay, we studied a little bit. Indeed, the degree is just a kind of subgraph, so you can ask more complicated questions, so that, as example, you can try to count subtree, but you can also try to evaluate the size of a dominating set. Giovanni was doing something like this to say, okay, if I want to dominate the network, how many nodes I need? Or you can ask also, and that's the second question. So it's difficult because we don't know how to compute quickly a dominating set. And the third question is to look at something even more complicated. It's not to simply solve optimization problem, is to look at some dynamic. So let's say I want two information flow are in the network. How do they behave? And is your random model, can you analyze it on your random model, and does it behave a bit like on Twitter? Or that would be question like this. Instead of simply looking at the degree distribution, or indeed you started because you did clustering, thing, which is more complicated than simply the degree distribution.
Yeah, so no, indeed, we didn't look at it. So I will focus, for instance, on what you talk about the flow in the graph and the models that have been presented. So we didn't look at it, but I think, of course, it's interesting also to study, to see how information propagates and so on. But I hope I won't say something stupid, but for me it's more the second step. Like, first of all, you have to build a network that will look like the real world network, and then once you have this random graph, you will look at how an information, for instance, propagates in this network and so on. And so here we are maybe more on the first step, which is building random graphs that are coherent. And then those random graphs might be used to study this flow. But so we didn't go to this step. Did you answer the question? Yeah. I'm not sure.
No, it's I don't know if and the last one was I skip all the other, was what, okay, in your PhD you did some engineering a little bit because you had simulation, programmation, modelization, some theory, probability theory, some programming. So what do you prefer, to define new model, to solve mathematical problem, to write code, to run actual experiment? That's
yeah.
What do you plan to do, or to keep everything together? I don't know. That's a question.
Yeah, actually,
personal question.
Yeah, that's more or less the answer. One thing that I really love during my thesis, and I think you've seen the manuscript, is that I really have to help to keep the theoretical part and the practical part, like doing a model or some computation or something, and I don't know why is it used for. I'm not really motivated by that, and on the contrary, just looking at other things too. But here, having the two parts, like the theoretical part and doing some model, but that will be useful, and I look at the real part and I study it. I really love the fact that I can have both of them, and I think I'm lucky to be at the correct team and at the INRIA, which had the data, the Twitter data, the Scopus data. So we might do some real things, some practical things, and also of course the theoretical background, which is really strong in the quality team. So I think I was lucky to have access to both those fields, and that's what I like.
Okay, and last one, I remember you had a nice model that indeed people mentioned bipartite graph, graph where you have people on interest, people on community, or people on celebrity, and you had one, I remember, with normal people on, let's say, celebrity or institution, like, the New York Times, blah, blah, or Mr. Obama, or whatever. And then you had that on what I think it was a very interesting way, because Google was doing that, search engine did that, and what became about this stuff?
Yeah, so indeed, we made that, and we didn't do for now. Maybe later, I listen about that. But yeah, we introduced another model at the beginning, but I was in internship for Twitter, because it was based on the idea that Twitter was both an interest and social network. And I had the idea to add two different types of nodes that would be celebrities and nodes that would be, let's say, random guys, lambda people. And the ways people can connect to each other would differ in that way. Like you had two types of edges, social edges that might be between anyone, and information edges that was from anyone, but necessarily going to celebrities. And I think the idea behind this model was nice too, to say, okay, we have two types of nodes and two types of edges, quite nice. But one of the main problems that led, so maybe we should have go further about it, but one of the main problems we have encountered is that we thus had two degree distributions, one for the interest part of the graph and one for the social graph. And when you were doing the sum of both of them, you hadn't a power law degree distribution, but more a sum of two power laws, and it wasn't really fitting with the reality. And so after that, we went to the clustering coefficient, and so we let this idea goes off. But yes, so for now, it's just asking to be open again and done better.
So it may re-emerge. Okay. Thank you.
Yeah.
Okay, I'm done. I mean, I will not keep the jury till 8 o'clock. So.
Thank you, Stéphane, for that. Okay, so my turn. So I won't ask many questions, Thibaud. So I wanted to join all the compliments that you got concerning the quality of your presentation, which I thought was really well prepared, and you really spent, you made a good balance between presentation of the context of your work and the technicality of some of the works, and I really enjoyed it. And I also wanted to congratulate you because as Stéphane has mentioned, you managed to bridge the gap, a gap in your work between some theoretical results that you obtain and some practical applications on real-world graphs, and that's something that's really rare. So congrats for that, and that's something I really enjoyed in your PhD. I have one on maybe it's, well, I have one mundane question at the end, but I have one technical question. Is first, I don't remember, sorry if I missed it, but I don't remember if you mentioned how much time it took to generate the graph that you simulated from the Twitter network.
Yeah, you mean check?
Yes,
this one on the right side. I think it took quite some time, like a few days.
Okay, I was wondering. And the second part of this question is what happens, so in this case you stop before you reach the number of nodes of Twitter, of your sample of Twitter. What happens if you want to generate a graph that is larger than your original graph? Is it possible?
Well, yeah, that's a good question. And
you should not be completely surprised by this question.
Yeah, that's indeed a good question, and that's one of the limitations, because of course we start from this degree distribution, and so the attachment function will go at most at this point, and actually it might even, here we see it stopped before, because once you have a zero, if we take back the formula from the theorem, here we can replace it with the sum with k going from 1 to I. We can say 1 minus so on. But when we have a zero, here we have a problem because we divide by 0. And we have to deal with that quite soon here.
Okay, so that's why it stops.
And so there is quite two answers, I think. The first one is how to deal with this, which is the first question. And here what we have done is what we interpolated between points. And to go even further, well, for sure, you can do it without the, I mean, Twitter has some information in practice, and you can't. The information is not contained in Twitter, so you can build something without information. So the best you can do is interpolate or suppose that, okay, maybe here it's a straight line, so we can say, okay, it will be a straight line until the end, and then you can go further. But of course, it's just a supposition because you don't have the information in Twitter. Yeah.
Okay.
That's the first thing. And maybe just to come back about this that took a few days, I think there is 2 algorithms that are able to generate that. The one I have used, I think, have a complexity in big O of n squared, and so it's quite long, but has a lot of networks. But I think when you have attachment functions that are only increasing, so without decreasing, you can have other algorithms that are in big O and n, just like Barabasi-Albert, with just like you can do with Barabasi-Albert, and it takes some memory. You have some memory complexity which is a little bit high, but not more than what you keep for your degrees. Maybe you will double your memory time, or so on. But for this, I couldn't apply it because it was decreasing, and same here. You couldn't do it for this, so it's only working in some cases.
Okay, thank you. And my more mundane question is, what are you doing after your PhD? If you already know.
Yeah, no, that's a good question, and I don't totally know. I had some. Actually, one of the for personal reason, I would like to stay where I live, so close to where I live, and so a postdoc is quite hard in that direction. So the quality team, and especially Frédéric and Nicolas, are also working with a startup which is in Avignon, and which is working on big graphs. And so for now, I have contacted them, and we will see. Maybe I will work with them, and maybe with INRIA. But it's just just a start. Nothing is done, so it's just the idea for later.
Okay, thank you. Well, all wishes for it to go well. Okay, so this concludes the first part of the defense. So I think the committee will go to another chat room to discuss. Okay, yeah. I see the link.
Okay, perfect. Okay, so thank you very much to everyone. Good deliberation. Bye. So I don't know if okay, perfect. Jean-Loup Guillaume is no, maybe I don't see. Jean-Loup Guillaume is still here. I don't know if it's just but maybe it's because he's here 2 times. I don't know if you hear me, Jean-Loup Guillaume, but the deliberation.
Thibaud, tu veux que je demande à Fred si Jean-Loup est bien avec lui? Ah bah non, Jean-Loup est là.
Parfait. Oui, bonjour. La salle de délibération vient d'ouvrir, et du coup, si vous voulez rejoindre pour délibérer, alors vous devriez recevoir, je pense, le lien bientôt.
Je crois que c'était ici, justement, qu'on délibérait.
Ah, non, justement, normalement, c'est dans une salle. Alors, attends, juste
oh, ok.
Ouais. Ah. Et si tu veux une autre salle? Ok. Alors, en fait, ce qui se passe, c'est qu'apparemment, comme vous êtes arrivé avec un autre compte, du coup, il faut que la première salle soit fermée puis réouverte. Vous pouvez pas forcément
It's here, it's here.
I'm definitely not interested in what's coming back.
You are not interested in the result, so you left.
Ok, donc je vais dire en français. I'll say it in French. Sorry, Pawel, but it's the customary for the audience. Donc, Thibaud, donc on a trouvé ta présentation extrêmement pédagogique et accessible et qu'elle démontrait à la fois la qualité de tes contributions et ton recul sur ton domaine. On a apprécié que tu aies choisi de te focaliser sur certaines contributions afin de pouvoir les présenter en détail et on a trouvé que tu avais réussi à présenter des contributions très techniques de manière simple et en communiquant des intuitions très claires. Tu as également réussi à nous donner une très bonne vision du spectre de tes travaux qui combinent des résultats fondamentaux remarquables mais également des implémentations et des expérimentations portant sur la modélisation des grands graphes. Tout ceci en visioconférence, donc c'est d'autant plus appréciable. On a posé de très nombreuses questions et sur des aspects différents de ton travail et on a beaucoup apprécié la qualité et la pertinence de tes réponses et les discussions qui en ont suivi. Tu as répondu de manière détaillée, claire et convaincante et tu as démontré par là que tu maîtrises complètement les aspects techniques de ton travail, mais aussi une très grande maturité et un grand recul sur ton domaine. Donc, pour toutes ces raisons, nous te décernons à l'unanimité le titre de docteur en informatique de l'Université Côte d'Azur.
Merci beaucoup, bien sûr. Du coup, alors, j'imagine que c'est à moi maintenant.
Si tu veux dire quelques mots, oui.
Ouais. Donc, merci beaucoup. Merci beaucoup. Merci à tous, à tous les membres du. Merci à tous les membres du jury d'avoir accepté des parties du jury, etc. Donc, merci beaucoup à vous tous. Merci beaucoup, évidemment, à Frédéric, je le sais, mais c'était vraiment, je pense, une chance immense que j'ai eu d'avoir comme directeur. C'est très bien passé, et c'était vraiment un grand plaisir. Et beaucoup, pour avoir discuté avec plusieurs doctorants, je me rends compte aussi de la chance que j'ai eu de l'avoir comme directeur sur plein d'aspects différents, autant techniques que humains. Merci aussi à Stéphane, le fermeur actuellement. Pareil pour son soutien et tout ça, et tous les autres co-auteurs aussi, donc etc. Et aussi Guillaume notamment Ducoff, qui du coup m'a accueilli un temps en Roumanie, alors un temps raccourci, parce qu'après avec le Covid, j'ai dû rentrer plus rapidement, mais quand même. Merci aussi. À l'équipe, à toute l'équipe Coati aussi, bien sûr, avec qui l'ambiance est vraiment super là-bas, et c'est une chance aussi, je trouve, d'avoir une équipe avec une bonne ambiance comme ça. Et aussi particulièrement à Johanna qui m'a aidé pour les cours, parce que j'ai donné aussi pas mal de cours ces différentes années, et notamment cette année, et du coup elle a vraiment fait la liaison avec l'IUT pour m'aider les cours, faire en sorte que ça se passe bien, et beaucoup déchargé sur ce quand c'est le travail, quelque chose de pas facile, donc voilà, merci beaucoup à elle aussi. Et puis après bien sûr à tous les extérieurs qui m'ont soutenu, les familles, amis et tout ça, donc ça je crois qu'on les prend tous, et merci bien sûr à tout cela aussi. Donc voilà.
Bravo, encore.
Bravo Thibaud.
Ouais, félicitations.
Bravo. Félicitations. Tu avais donné des cours, c'est pour ça que c'était si bien présenté, on comprend.
Si, soit ça, soit l'inverse, on ne sait pas.
Ah, mais tu as retrouvé Thibaut. C'est incroyable. Thibaut.
Ouais, non, c'est ça. J'étais en inter cette année, donc j'avais pas mal de cours. C'était bien aussi.
Ouais. Bon, mais il est où le pot maintenant?
Ouais, c'est lundi, le pot, c'est où?
Pour l'instant, ouais. C'est que...
mardi, il y a une espèce de pot chez Nicolas, là, apparemment.
Ah oui, c'est vrai.
Pour les Azuréens, uniquement.
Oui, ça va être compliqué de rassembler tout le monde.
Peut-être quelques mots en anglais pour les Anglais?
For Pawel, I don't know, yeah, so if you follow what to say, so yeah, just just that I had the doctorate, so no, I don't know what to say. Yeah, thank you.
Yeah, thank you so much. It was a pleasure. Yeah, so I didn't follow all the discussions, of course, you had in French, but I am assuming, you know, it was all good. So everything was perfect from my perspective. So thank you so much for, you know, great contribution to the field and opening up a lot of questions. And yeah, I'm sure we'll be reusing some of your observations in the future for sure.
Nice.
Thank you so much.
So thank you for having accepted to be here. I had to wake up early for this PhD too, because it's way earlier for you. So yes.
Oh, it wasn't too bad. Yeah, I think I gave a few talks in China and India recently, so you know I had to wake up in the middle of the night, for example, right? But yeah, this one is 8 a.m., so it's perfect. I usually start at 9, but yeah, 8 is equally good.
Yeah, okay, yeah. Not the worst candidate, PhD candidate for that.
Yeah, no worries. Yeah, it wasn't bad.
Okay, great.
Okay.
Well, thanks a lot. Yeah, I wanted also, of course, to thank all the jury members and for all the nice discussion. And yeah, we'll be keep in touch for the future discussions.
Yes, of course.
Yes.
And thank you also, Clémence, for having accepted to be president of the jury. I heard it was not that easy decision. Thank you also.
No, not a
You
problem.
cannot imagine how easy it was for her.
No, she's born to be jury president.
No, it's just because I do it all the time, so I'm getting good at it. But if you guys had more practice, I'm sure you'd be as efficient as I was.
Okay. Especially on Zoom, it's even harder.
Okay. Thank you, everyone.
Yes, thank you. Félicitations encore, Thibaud.
Félicitations, Thibaud. Ciao.
Et profite bien de tes vacances. Hein. Profite,
ouais, merci beaucoup.
Bon repos, bon été. À bientôt.
À bientôt, tout le monde.
Au revoir.
Bientôt,
Au revoir tout le monde. Ciao, ciao. Bye bye.
Ciao.
Et Jean-Loup, il est parti. Parce qu'on espère le voir à Nantes, hein, Jean-Loup, quand même.
À Nantes? Pourquoi à Nantes, David?
Parce qu'il y a Algotel à Nantes.
Ah, ça existe encore, Algotel? Moi, je croyais que c'était dissous dans le Covid.
Non, c'est pas le Nantes, d'ailleurs, c'est la Rochelle. C'est eux qui organisent.
Ah, oui, c'est l'université.
Je te fais des bisous, Thibaut, j'y vais.
Ça marche.
Gros bisous, bravo encore. Super. C'est le meilleur.
Ouais, c'est vrai.
Gentil. À bientôt.
Bientôt.
Bon, bah, à bientôt, ouais.
Bon, allez, au revoir. À lundi.
À bientôt, ouais.
À lundi, probablement.
On te revoit quand même, on te revoit.
Oui, c'est ça.
Oui.
Il revient quand même.
Ah, tu passes, Thibaut, quand même? Tu viens au barbecue de Nico, là, ou pas? Ou tu peux pas?
Je vois, j'ai pas regardé les dates.
Ça pourrait être une occasion, puisque c'est mardi, je crois.
De toute façon, je vais repasser, parce qu'il faut que je fasse deux trucs pour le papier du 30, là, le papier de mascotte. Mais je ne sais pas si je viens lundi ou mardi, parce que j'ai un peu des copies à corriger, en fait. J'ai des examens, et du coup, j'ai tout repoussé à ce week-end. Mais
t'es loin, là? T'es où, en fait?
Non, je suis pas loin, je suis à côté. Mais c'est juste si lundi, je suis encore dans les copies, je viendrai plutôt mardi, sinon mardi, quoi.
Oui, on ne sait quatre. Ne te stresse pas, là, ça va.
Ouais.
Profite-en un peu, quoi.
Avant, c'est ça.
Ouais.
Ouais, en tout cas, la semaine prochaine, je repasserai.
Ok. Bon, on t'embête pas plus, faites ça.
Ouais,
les amis, la famille.
Les amis, ouais, c'est cool.
Ouais.
C'est sympa. Puis pour la gestion du Zoom aussi, ils étaient au taquet.
Ouais.
Et donc, j'ai compris, le papier avec Guillaume, il sera jamais fini, puisqu'il finit sa thèse, là, c'est foutu maintenant.
Puis Guillaume a des enfants, et puis...
C'est à cause de Guillaume, tout ça.
Trop d'enfants, ça bloque la recherche, les enfants.
Ouais.
Il essaye de passer par juillet, Guillaume. Il cherche un appart.
Essaye de passer quoi?
Si vous lisiez vos mails, je vous ai forwardé un mail de Guillaume. Il cherche un appart.
Oui, moi je fuis la Côte d'Azur, il y a Guillaume qui arrive.
On va le séquestrer dans notre appart pour qu'il finisse le. Donc il travaille.
Voilà, donc c'est ça. C'est à vous de lui proposer un logement pour 10 jours fin juillet, c'est bon, quoi.
On va voir ça, ouais.
Bon, bah, très bien.
Ok. Bon, bah, allez, ciao, ciao Thibaud, allez.
Ciao.
Encore.
Et à bientôt.
À bientôt, ouais. Ciao.
Allez. Comment on quitte ça là?